wonderful highs then.
Hello. Okay, are we good to go?
Yes, I think so. That would be good.
All right, so I'll try to get back on time too. That's no problem. So I think I was talking about representations of subsets. So we had this problem. We want to compute the reachable set of states. We want to do this in high dimensions, and we want to do certain operations efficiently, right? And so I was talking about, okay, we could represent a set of states as a box where you have a lower bound and an upper bound for each state variable xi. The downside of this is when you perform a linear transformation of a set like a box, the result is no longer a box, right? Like we had in the example, we had this, rotate counterclockwise mode where the whole box is sort of rotated after each step. And so representation as a box, you would accumulate error after each step, which is called wrapping effect error, which is sort of bad for the accuracy of the computation. So there's other types of representations you can consider. So typical representations from computational geometry are like vertex polytopes, which is a V polytope is a convex hull of a set of points. And then to advance time, what you do is you take each of the vertices and you propagate them through the differential equations, which you can do, right? Because we had this, you can either use a numerical integration tool, or you could use this matrix exponential thing that I described earlier. The downside is the number of points m can grow very large, especially when the number of dimensions is high. So even a simple set like a box, in 2 dimensions, you have a square, so there's 4 vertices. In 3 dimensions, you have a cube, so now there's 8 vertices. And every time you add another dimension, you end up getting like 2 to the n vertices. So, once you get to, hundreds of dimensions, that you might have millions or billions of vertices you need to do, and then the operations become very slow. So V polytopes don't work. H polytopes is another representation. So this is a polytope represented as a conjunction of half spaces. The downside of this is, in general, when you have an H polytope, to propagate it through differential equations, there's no way to do this except converting it to a V polytope and then going back to an H polytope, especially when the linear transformation that's not invertible. That's really the problematic case. So other representations that are sort of good ideas that I'll mention here in the context of both CPS verification and neural network verification are zonotopes and star sets. So we'll have some intuition, I think, on the next slide, but here's the mathematical definition. So a zonotope, you can think of it as you have this point alpha inside a p-dimensional space, and then you compute an affine transformation of that point. So you take alpha, you multiply it by matrix V and add some offset C. And then you have this final point X, and then X is in some n-dimensional space. So N and P can be different because this matrix doesn't need to be a square matrix. So linear star sets or AH polytopes or affine forms or constrained zonotopes, it's all the same name for this data structure, which is very similar to a zonotope, except for zonotopes, alpha was inside the unit box. Now alpha is inside an H polytope. So you have a point alpha inside some polytope defined by half spaces, and then you perform an affine transformation at that point. So the intuition is a zonotope is an affine transformation of a point from a p-dimensional unit box to an n-dimensional space. So you start with if n and p are both 2, I can plot it. So that's sort of a nice case. So you start with a point alpha, then you perform this affine transformation, which is just a linear transformation plus an offset. And you end up with some other point x. And the linear star set, you start with a point inside a H polytope, so defined by linear constraints. So you can imagine maybe you have 3 half spaces that define a triangle, and your alpha point is inside the triangle, and then you perform an affine transformation of the triangle here. So it's similar to a zonotope, but a little bit more expressive, right? So you couldn't represent a triangle using a zonotope because a zonotope is always going to be centrally symmetric because of this property that the sort of the domain has to be this p-dimensional unit box. So it's a little bit more expressive. And you can do a couple different operations with this too. So in particular, you can do linear transformation efficiently. So this essentially comes down to matrix multiplication. So you modify the affine transformation part. That's how you can do a linear transformation with linear star set. You can do intersection checking because you can put this definition into a linear program. So this is the definition of a star set. It's all linear constraints, and linear programming will scale to hundreds or thousands of dimensions. Like you can actually solve those types of problems. So that's nice, and you can actually compute intersections. And this is just a little bit of linear algebra. It's basically just variable substitution, but it boils down to basically matrix vector multiplication. That's the efficiency of this too. And you're modifying the half space polytope while keeping the affine transformation part the same. So you can actually perform in reasonably high dimensions linear transformation, intersection checking, optimization, intersection computation as well. But there's symbolic and numeric concerns for each of these operations, right? So if you're doing matrix multiplication, it's most tools are doing this numerically. So maybe you want to do this with sort of outward rounding. There may be conditioning issues if you have to do this repeatedly. Maybe you want to recompute the matrix exponential after a certain number of steps instead of just continuously just multiplying by a matrix. Is everything okay? It says participants can now see your screen, so hopefully it's still sharing, right? Okay, I'm going to keep going.
It's all fine. It's all fine. Thanks.
Okay, great. I'm just cautious. It disappeared last time. Intersection checking, right? So linear programming, this is great because we have this nice efficient algorithm, but it's a numerical algorithm, right? So are there efficient ways to do guaranteed linear programming? Or maybe I think I think it's okay. There was some audio noise, but okay, yeah, linear programming. So it works efficiently, right? But the accuracy of a linear programming tool, it's usually like 10 to the minus 7 or something like that. It's not even floating point accuracy. It's a lot less. It's not symbolic accuracy. And there's instability issues with linear programming practice. So when you're doing these reachability methods, sometimes the solvers will print stability issues where if you have boundaries that are really close to each other, the solvers will give you errors. That's kind of bad for a verification tool, right? You don't want that. You want some sort of symbolic methods that give you guaranteed solutions, but those are a lot slower, right? So this is the trade-off. And intersection, right? So this is something interesting that come up. So if you learn about linear programming, sort of from a symbolic standpoint, right? If you took a set and you optimized it, I had a set of linear constraints, and let's say I got an optimization result that was greater than 0, right? And then I added an intersection that said, let's say in my result in the optimization, I maximized X and I got X is greater than 0 as the result. Then I added a constraint that said X is greater than 0. And then I took that set and I tried to optimize it. At that point, the LP solver sometimes tells you the set is infeasible, which is really strange, right? You would think you've already optimized it. You've proven there's a point in the set where X is greater than 0. Why is it infeasible when I add that constraint? And so part of this is due to numerics issues. So again, the accuracy of an LP solver might be like 10 to the minus 6 or 10 to the minus 7. If my optimal point is within that, like it's 10 to, the maximum value of X is 10 to the minus 7, then I add that constraint that X is greater than 0, it's possible that the LP will come out as infeasible at that point. It's sort of like within its accuracy bound. But that's tricky when you're writing the code, right? You're designing these algorithms. That's something very unexpected, right? There's also things like, there's different parameters. You can switch from primal LP to dual LP, and sometimes that switches it back to be feasible, right? So it's not great from a formal methods perspective, but if you want, fast and efficient solvers, you still have to use these types of numeric tools. So I don't have really great solutions for this. So I only have about 5 minutes left, but I do want to explain a little bit how these same data structures can be applied at least to neural network verification. So when you have a neural network, you have sort of there's obviously lots of types of neural networks, but sort of the basic type I think you learn about in the first couple lessons, let's say on deep neural networks, are ones where you have fully connected layers, possibly with hidden units, and maybe just general nonlinear activation functions, sort of simple ones. So in order to execute one of these, say you just wanted to execute this particular input point, you would have to be able to apply affine transformations, which is multiplying by the weights matrix and adding the bias vector. That's an affine transformation. And then you need to apply an activation function. And then you just repeat these. So you start with, let's say, if you have 2 inputs, you start with a 2-dimensional point. You apply an affine transformation. You go to a 3-dimensional space. You apply the activation function on each of those dimensions individually. And then you sort of repeat the process. You do another affine transformation to get to the input of the next layer. You apply the activation function to get to the output of the next layer. And then you sort of repeat, affine transformation, activation function, and so on, until you get to the output. So when we talk about neural network verification, there's lots of different versions of this. But the sort of basic version is the open loop problem, where you're given an input set and you want to prove something about the output set. For example, given that the inputs are within some ranges, can you prove that, let's say output 1 is greater than all of the other outputs? So this would be sort of like the classification doesn't change under small perturbances of the inputs. And so if you want to do this reachability-based analysis method for neural networks, you could do it with set-based operations. So you start with a set of states in, let's say, a two-dimensional space. You apply an affine transformation to that set, and then you apply an activation function to each dimension of the set. And then again, you just sort of repeat these operations over and over again. And so affine transformations, we already sort of talked about that before in the context of cyber-physical systems. That becomes for zonotopes and linear star sets, this is matrix-matrix multiplication. So what about activation functions? So the simplest type of activation function is a Rayleigh activation function, where the output is just the maximum of the input and 0. So if the x-axis is the input, the y-axis is the output. This is sort of what your function output looks like in one dimension. And so if Li is the minimum possible input to the neuron and Ui is the upper bound of the input to the neuron, then the output will have this type of non-convex shape, which is a little bit difficult to handle. You can't represent this exactly with star sets or zonotopes because it's non-convex, right? It's enough. But it's not always this difficult, right? If the lower bound of the inputs is greater than 0, this is now an identity transformation. This is, you can represent this exactly with star sets and zonotopes. Similarly, if it's strictly negative, this is just a projection to 0 for one dimension, which is you can do it in terms of a matrix operation. And sort of the difficult case is really where the lower bound is less than 0 and the upper bound is greater than 0. But here you can split the set because with star sets, you can compute intersections. So you could split it into two parts where each of the two parts is a linear operation. Or you could consider over approximations. Maybe you don't want to split because now you have to work with two sets. You just want to work with a single set. So you could instead compute this convex over approximation and again represent this with something like star sets. Or if you want to use zonotopes that have to be centrally symmetric, you can't represent triangles, but you could represent this other set, which you could do with a zonotope, which is again an over approximation of the real output. But this could again be useful for proving properties in certain cases. And so there's numerical issues with these two. So in particular, we need outer approximations for these lower and upper bounds to compute over approximations exactly. So the case I described before too, where say you computed the upper bound and the upper bound was greater than 0, but it was just slightly greater than 0. It was like 10 to the minus 7. So then maybe you added this intersection that x is greater than 0 to get this red set. But now the LP solver tells you it's infeasible too. So you have to sort of double check these things every time you sort of add constraints too. So there's numeric issues that come up with this verification process. But again, because we're able to use star sets and to efficiently perform affine transformation, optimization, and intersection, you can actually do analysis exactly for neural networks. And this isn't just fully connected neural networks. You can also handle like convolutional layers or average max pooling layers using this exact approach. And there's extension also to other activation functions where you can maybe support over approximations. There's still numeric issues here too. Even executing a neural network from a particular input set is not completely well defined because the semantics of floating point operations on GPUs are intentionally sort of left up to the implementation. In terms of when you're doing a matrix-matrix operation, you could multiply and then sum terms together, or you could sort of incrementally sum terms when you're doing sort of these matrix operations. And they let GPUs choose how to do this for efficiency. But as a formal methods person, this means that there's some, the semantics are not precisely defined. You kind of really would want to handle both of these things to sort of have a guarantee on what the output should be. And this is not something that's sort of, it's not deterministic, right? Because it's not exactly defined what's the correct answer. And this can lead to floating point issues, which could lead to a different output potentially. So I think this is maybe enough to just show you that there's sort of interesting set-based operations you could do. I'm going to skip over a lot of the sort of optimizations that you could see to make this method actually more efficient. So the basic approach, it will work, but it's not going to be fast, I think. And so I think there's a lot of work on how to make this faster and how to work for larger systems. One other thing I'll mention is that this is sort of an active area of research. So there's a neural network verification competition. We just finished the second one a couple of weeks ago, where we evaluated maybe 10 or so different tools on different benchmarks for neural network verification from around the world. And so this is something, if you want to get into this area, you could definitely check out our report for this. So it's called sort of VNNComp. And we, on common hardware evaluated 12 different tools using common benchmarks. And you could see that, which methods basically perform faster on objective benchmarks. So this is great if you're developing a tool. You could evaluate your tool on these sort of common benchmarks and sort of see if there's actual improvement or not too. And so this reachability-based method for certain categories performed very well. So there was this particular ACAS-XE benchmark suite where this Nnv tool that was based on this reachability method using star sets that I described actually performed the fastest and verified the most benchmarks. So these are sort of state-of-the-art methods, I would say. And so that's essentially it, though. So I wanted to mention that these, flow pipe construction reachability-based methods are very useful for CPS verification, but also neural network verification. But sort of as I got to mention in the talk too, there's numeric issues sort of all over the place, matrix exponentials or LP solving that sort of come up and can sort of erode the guarantees you would expect from formal verification methods. And so this is sort of a really challenged question when you're doing research is, I could go back and do numerics correctly, use a symbolic LP solver, but then that would slow things down. And there's still issues now in terms of scaling up to sort of large neural networks. For example, even in the competition, we didn't verify any ImageNet networks because those are much larger and the methods really don't scale well enough yet. So, what's more important? Should we first scale to the correct problem size, or should we be really more rigorous in terms of some of these numeric operations we're doing? And I don't know. There's no exact answer to this too. Obviously, you need a balance of both, but it's something to consider when you're doing research. So I'll leave it at that, and I'm happy to answer any questions people have. Thank you.
Thank you very much, Stan, for this wonderful talk. Do we have questions from the audience? So please feel free to use the chat function to post your question if you're an attendee. If you're a panelist, of course, you can just speak. In the meanwhile, while we're waiting for maybe more questions, I would like to ask about these different state set representations and the effect the choice has on the numerical precision. What is your experience with that? What would you recommend for a good middle ground?
Mm-hmm. Yeah, so in order to do analysis efficiently, typically use a combination of representations. So the two I had mentioned in this talk were these linear star sets and zonotopes. So zonotopes are actually faster than star sets, but you can't perform intersections with them, at least not exactly. And so in terms of numeric issues, those zonotopes are a little bit better because you don't need linear programming. I think one real bottleneck is, guaranteed linear programming is something you would want if you're dealing with star sets. Whereas with the zonotopes, I've seen papers where they try to take into account floating point error, and they can actually do outward rounding with them. So you get sort of stronger numeric guarantees. But then there's still the question of, okay, what does the GPU actually do? It doesn't compute, symbolic results when you're doing a matrix multiplication. It's actually going to use floating points, and it's going to round. And it's probably using single precision instead of double precision because you get a close enough result a lot faster, right? You can handle larger networks. So then, the goal shouldn't be symbolically correct answers. It should be answers that contain whatever the GPU is doing. So if it's rounding, you want to be rounding as well. So that's a kind of a difficult problem. So with zonotopes, you can maybe bloat things a little bit, and I think they're sort of better suited for numerics. But the downside will be your analysis will be less accurate. Yeah, I see. So we often use polytopes, which is of course horribly slow, and to avoid convergence between V and H polytopes, we were thinking about maintaining a double representation. Does this also make sense with other more advanced representations? Have you tried this? So the issue I would see with double representations, I mean, one is the conversion issue, but even without the conversion issue, sometimes the number of points can grow to be very large, especially in high dimensions. So I think I have, there's an animation here. I don't know if it's going to play, but this is the propagation of, this is an execution of a neural network comparing random points in the initial set versus the exact output set computed using this, AH polytope or star set representation. And you can see that sort of outward gray set gets very complicated. So this is just 2D projections, but a lot of these are sort of 50 dimensional sets projected down to 2 dimensions. And so I think by the final layer in this sort of simple example, it's basically a union of 9,000 different polytopes, and sometimes they're in 50 dimensions, right? So even with something like a double representation, the vertex part of the representation would be sort of very large, and then the H part of the representation would be hard to. Well, I guess you could extract it from the V representation. So you can avoid some issues by maintaining both representations, but this one's a simple example, right? So this was an example where I could do exact enumeration. There's a lot of examples where you can't, just because the number of sets grows to like 1 billion different sets, and then my analysis, it just doesn't finish. So you end up having to use over approximation if you want to hope of verifying any properties. Yeah, so I don't know. That's not a great answer, but it's still challenging.
Yeah, wonderful. Thanks a lot. Are there questions from the audience? Yeah, there is one. Probably I will just read it. It's from Samuel Teuber. Thank you for the question. So it says, thank you for the great talk summarizing the numerical issues in neural network verification. Have you considered a two-step approach when you first verify the neural network using the outlined methods and then try to prove that verification results are to some extent immune to floating point errors that might have occurred in the verification process? I'm not sure if this will even be feasible, but maybe that's an idea.
Yes, that's a great idea. And I think actually that's probably the way to do it, is maybe use these numerical methods that are sort of approximative to construct sort of like a proof template of proving properties about the system, then sort of then extract all the proof conditions you need to use that you could use some sort of formal verification tool that reasons symbolically over the variables to prove the properties you're interested about the network. So first run it numerically, right? And then extract the symbolic equations that need to be true, and then check them. And if any of them don't meet, then like augment the proof with more numerical computation. I think that's probably that's a very promising approach, I think, to doing it. The state of the tools right now, so we had 12 tools in BNN-Conf that we analyzed. Nobody's producing this sort of external proof like you get with like a SAT solver or SMT solver that maybe you can check for correctness. It's like the tools aren't there yet. So maybe in a couple of years, when we start producing these external proofs, that type of approach could be doable. Yeah, I think it's a good idea.
Thank you. So I hope this answers your question, Samuel. If not, just type another one. Then there is a question from Stefan Schupp, and he's asking, are there any approaches to deal with the exponential number of sets you need to track during computation when splitting during the application of Rayleigh activation functions?
Yes. So I mentioned a little bit where you had the Rayleigh, you could split it and then you're doing exact analysis. But the other choice is you can over approximate it. And so either with that triangle over approximation, which you could use star sets for, or polytopes, or you could use the zonotope over approximation. So those ones don't require splitting, but the downside is they accumulate error. So you have this trade-off of you have these exact methods that are slow and you have over approximative methods that are fast, but sometimes there's too much error and you have to balance between the two of these. And so this comes up both in CPS verification as well as neural network verification. And I think even software verification has the same problems. It's like you have speed and you have accuracy, and choosing the correct level of abstraction is the sort of critical challenge. And so we've been looking at different ways to do this, like some standard ways are like counterexample guided abstraction refinement, right? Where you start out with maybe a chorus abstraction, you over approximate everywhere, you try to prove the property. If it doesn't work, then you go back and you refine. Maybe you split a couple times, but not every time. And I think that's it's still not clear the best way to do that, but that's at least one approach where you can balance between sort of the accuracy of star sets without having a sort of exponential blow up in the number of states.
Thanks for clarifying, Stefan says. And then there is a question by Eugene Azara. Do you think that ellipsoids and level set representation for sets have no perspectives? I mean, are we obliged to stay within variants of polytopes?
So the issue with level set methods usually is, the dimensionality, I guess. So I think you might be able to do something if the number of inputs you're analyzing is small. Like if you're only analyzing, let's say, 3 inputs of uncertainty. So maybe you have a large, some properties for image classification networks could be like adversarial examples where you only modify a couple of the pixels. So let's say I'm only modifying 3 pixels. So I have 3 dimensions of uncertainty. Perhaps level set methods could play a role actually in analyzing those types of neural networks. I haven't really seen too many works exploring that area, but I think it's that there could be potential there. If you told me to investigate level set methods for neural network verification, that's the first place I would sort of look. And maybe some sort of representation actually, where you have you take the same trick that we're using with star sets, which is you keep the domain representation separate from the affine transformation part. So you have some level set representation, and you have the affine transformation part, and keep those two separate instead of actually trying to represent the set, because the set in each of the hidden layers is going to be in a high dimensional space, and so you'll run into problems. But if you just if you transform it back to the original space, you could keep it in low 3 dimensions or something like that, where it's sort of more feasible to do analysis.
Thank you for this clarification. Thanks a lot for the wonderful talk. I'm not sure how we can thank you. I'll clap. Thanks a lot. And I'm sure Stan will be around to answer further questions if you post them in the chat. So the next speaker will be Tom Beidings. He's a PhD student at Radboud University Nijmegen. I assume you're a PhD student with Marielle, is that correct?
Yes, that's correct indeed.
Good. So you can share your slides. That's wonderful. The floor is yours.
Great. Can everybody see my screen and hear me loud and clearly?
Yes, I can.
Okay, great. Yeah, thanks. And thanks as well for organizing this workshop. So indeed, my name is Tom Beidings, and I'm a PhD student at Radboud University. Under supervision of Marielle Stoelinga indeed, and under supervision of Niels Jansen, who will be one of the invited speakers later today as well. And today I'll be presenting all about our ongoing research with our other co-authors, namely Alessandro Abate, Dave Parker, and Hassan Poonawala. So I will, I will start the presentation with kind of an intuitive introduction of the kind of problems that we're trying to solve in this work. So consider that we want to fly a UAV or a drone, and we want to do that safely. So obviously that means we want to fly from some point A to some point B, which is the goal region. And at the same time, we want to avoid hitting any obstacles or critical regions. On top of that, we consider a finite time horizon within which we want to arrive at our goal. And finally, but quite importantly to consider, we want to consider the effect of uncertainty in this problem, which can be caused by wind or turbulence, and this may affect the state and the velocity of this drone. And then the problem that we want to solve is basically that we want to compute a controller for this drone under which the probability to reach the goal is above a given threshold value. So that means, and that's quite important to note, that we're not searching for a globally optimal solution, but we are rather searching for a suitable controller with performance guarantees. Because if the kind of threshold value by which we can guarantee to reach the goal is not high enough, then it may be in fact better to not do the task at all, rather than having a high probability of crashing. All right, first step, of course, in solving such a problem may be to derive a mathematical model of it. And in this work, we consider linear dynamical models, which in our case are discrete time and continuous state. So here we have a continuous state vector x of k, which models the position and the velocity of the drone at some discrete time k. And the state at time k plus 1 is then computed as a function of the previous state plus some influence of the control input, which is derived by the controller, plus a deterministic disturbance at that time k, and finally an additive stochastic term which models the process noise. And in a lot of research, it's typically assumed that this process noise follows a nice Gaussian distribution. But the problem is that in reality, and for example, when considering things like turbulence, the process noise does not have a nice Gaussian distribution. And that's why in this work, we were especially trying to drop the assumption of having Gaussian noise. So that basically means that we have two different issues to deal with. So first of all, there's the issue that due to the process noise, the outcome of a specific control input is uncertain. And second of all, the probability density function itself of this process noise is also unknown. So we have to deal with both these issues. And although we do assume that the distribution of the noise is unknown, we do assume that we have access to samples of it. And this may be from historical or experimental data, or maybe from some high fidelity simulation model. And here the main assumption that we make is that the process noise is stochastic and is independent of the state and time. So essentially this means that we are able to obtain identically distributed and independent samples of the noise. So in the end, that would look something like this. So if we have attempted a specific transition for this drone already multiple times in the past, then every of these times we may observe a transition to a slightly different point than our target point actually was. And the discrepancy between the starting point and the actual point where we ended up, that is then this sample of the noise. And then we have a set of these samples based on which we need to solve our problem. All right, so in this work, we essentially propose an iterative problem solving scheme that is shown here on the screen, and I will go through it step by step in the next few slides. But the fundamental concept of this approach is that we compute a finite state abstraction of this continuous dynamical system as a Markov decision process. And in particular, we consider a Markov decision process, or MDP, which has intervals of probabilities rather than precise transition probabilities. And we do this to accommodate for epistemic uncertainty with respect to the transition probabilities. Then when we have defined this finite state abstraction, we feed it to a model checker. In our case, we use Prism. And here we can compute optimal reachability probabilities for specific properties on this interval MDP or IMDP. And finally, we then use the resulting optimal policy from this model checking process to compute a controller for this dynamical system. And here we have the very important but very nice property that due to the nature of our abstraction, the reachability guarantees that we obtain on the abstract IMDP, they carry over with high confidence to this dynamical system. So that in the end essentially means that we can synthesize controllers for these dynamical systems with unknown distribution of the noise, for which we provide a priori performance guarantees. All right, so let's now briefly look into how we actually derive this finite state abstraction itself. So as shown here in this figure, we kind of start with a continuous state space, and we want to partition this continuous state space into a set of convex regions, convex polytopes, in fact. And every region of this partition then corresponds to a state, a discrete state of this MDP. Then the actions of the Markov decision process, they correspond to control inputs that induce transitions between these regions. And because of the process noise, these actions are stochastic as well. And because we want our abstraction to be a faithful representation of the dynamical system, we also impose a certain constraint, which basically ensures that actions in the abstraction are only enabled if there exists an equivalent control input that would induce the same transition for the continuous system. Well, finally, we want, of course, to define the transition probabilities for this Markov decision process. But because this requires integration of the distribution over the successor states, and because this, in fact, requires the knowledge of the process noise distribution, this is not directly possible. So instead of that, we use a sampling-based approach to compute intervals of probabilities. And in fact, or in particular, we use n samples of the noise to compute probably approximately correct or PEC probability intervals where we specify a certain confidence level beta. And we then want to obtain probability intervals that contain the true transition probability of every transition with at least 1 minus this confidence level beta. And while I will not go into much more detail about how specifically we obtain these intervals, we use a variant of the scenario approach or scenario optimization, which is essentially a method to deal with stochastic convex optimization in a data-driven fashion. And here we exploit the fact that we can reformulate the problem of finding a transition probability. We can reformulate it as such a stochastic optimization program. Finally, we also propose kind of an iterative loop within our abstraction scheme, which is actually should be here in this figure. And by means of this iterative loop, we can iteratively improve the quality of the abstraction if needed. And by this, I mean that we can tighten the probability intervals by using more samples of the noise. So this is quite, kind of an intuitive result that if we have more observations of the noise, we can actually obtain tighter intervals on the transition probabilities. And this is shown here in this figure on the right for a just one dummy transition, which has a true probability of 0.25. And it's clearly visible that indeed the probability intervals become more tight when we use more samples of the noise. All right, so when we then have defined our abstraction, we want to optimize for, in our case, a step-bounded reachability property. And we do that in the model checker Prism. And essentially, we want to maximize the reachability probability, which is written as here. And we want to maximize over the set of available actions, while we minimize over the probability intervals of the interval NVP. So by doing so, we actually obtain conservative or lower bound reachability guarantees on this interval MDP. And we also obtain the corresponding optimal policy by star, which is in our case, a mapping from a sequence of states to the set of actions. And then we can actually do either of two things. So if our reachability guarantees are insufficient and we want to improve the abstraction, we can go back here and we can improve the abstraction as I told in the previous slides. The other option that we have is, okay, if we say it's sufficient, then we use the optimal policy, we extract it, and we can actually use it to compute a piecewise linear controller for this dynamical system. And here the actual most important property, as I told before, is that with high confidence, the reachability guarantees that we obtain in the discrete domain, they actually carry over as lower bound guarantees on the dynamical system. And that's in the end what we need to solve our problem. All right, so as a last part of this presentation, I will show a few numerical results obtained from applying our method. So the first example that we consider is kind of a similar motion planning example as in the introduction. So here again, we have a drone or a UAV, which needs to fly from some initial position to this green region. And it needs to do so without running into the red obstacles. And actually these blue lines are already kind of sample trajectories under the controller that's derived in the end when we have solved this problem. And we consider turbulence as an uncertain factor that affects the state of the system. And the main question is then, can we compute a controller that guarantees that the probability to reach the goal is above 75%? And the 75% is really a design parameter which can easily be changed if necessary. Well, we can model this system in our case as a 6-dimensional system, and we create a partition into around 43,000 regions, and we apply our method with increasingly more samples of the noise to iteratively improve the quality of the abstraction. So when we have a look at the results, it basically looks as follows. So this left figure is the one which was already shown on the previous slide. But as I mentioned, the blue trajectories are sample trajectories under the derived optimal controller. And well, the goal in the end is that, of course, at least 75% of these trajectories should reach the goal safely. But what's actually even more important, I think, is this plot on the right, because what this shows is, as the solid blue line, the reachability guarantee that is obtained from solving the abstract interval MDP that we obtain, while the dashed line shows the empirical performance under the corresponding controller on the dynamical system. So this is really the simulated performance. And what we wanted to obtain in the end is that this solid line is a lower bound on the dashed line, meaning that we have a lower bound on a lower bound reachability guarantee a priori. When we compare that, in fact, or we did also compare that to kind of a more naive approach where we would not use intervals of probabilities, but where we rather use approximate transition probabilities. So what that means is that we obtain a regular MDP with precise transition probabilities. But when we do the same comparison between the reachability guarantee itself and the empirical performance, we actually see that the empirical performance is much lower than the reachability guarantee obtained from PRISM in our case. And that's quite bad, of course, in the context of safety. All right, as a last slide before the conclusion, we also performed a comparison between our method and Stochastic, which is another tool for the analysis of stochastic systems based on formal abstractions. And similar as we do, also Stochastic uses interval MDPs. But the main difference is that Stochastic requires full knowledge of the noise model, while we only use samples of the noise. But in return of that, also Stochastic is able to give kind of straight probabilistic results, while we only can provide PEC guarantees on the results. All right, so we did this comparison on a simple temperature control problem, where there is a single room which needs to be heated to exactly a temperature of 21 degrees Celsius. And as you can see, on the left is our method, and on the right is Stochastic. As you can see, the results qualitatively actually look quite similar. And it is indeed the case that overall Stochastic may be able to obtain a bit stronger probabilistic reachability guarantees. But on the other hand, it requires the full knowledge of the noise model. So essentially, this kind of tells us that even though we do not have this explicit representation of the process noise, we can still do quite well in terms of guaranteeing reachability. All right, so to conclude, what are kind of the main takeaways of what I talked about? So we proposed a sampling-based approach for robust control of noisy dynamical systems. And we use this method to compute controllers with probably approximately correct or PEC guarantees on the actual performance. And finally, we observed that interval MDPs yield stronger or actually safer guarantees than when we would use a naive MDP abstraction. So as a few pointers for kind of current research, we're looking into more like adaptive state-space discretization schemes, because this would allow kind of a trade-off between the accuracy and complexity of the problem. We're looking into extensions towards nonlinear systems with nonlinear dynamics, and finally also problems with partial state observability. So thanks a lot for listening today, and I'm happy to hear if there are any questions, and otherwise you can reach me on this email address. So thank you.
Thank you, Tom, for this wonderful presentation. Again, please feel free to post your questions in the chat or in the question and answers. In the meantime, I would like to ask, so you've used PRISM for that. Would there have been, oh God, my English, other options to PRISM? just curious which tools you could have used.
I'm not sure, in fact. For this, we in fact had the support of Dave Parker, who actually helped us in tailoring a version of Prism such that it can handle interval Markov decision processes. So I think it's not kind of included in the base version of Prism yet. But I think the algorithm in the end that's being used is kind of a robust value iteration algorithm. So of course, yeah, probably it could be also implemented in similar tools. But we didn't really explore that yet, no.
Okay, I see. And do you expect that nonlinear behavior will have a huge impact on the interval MDPs?
Yeah, I think the main difficulty is in fact to compute which actions should be enabled in the abstraction. Because essentially what we, I didn't really dive into detail about that, but what we essentially do to compute the set of enabled actions in the abstraction is that we kind of compute the inverse dynamics of this linear dynamical system, and we kind of obtain the backwards reachable set, and every region of the partition that is then contained within this backward reachable set is then a region in which that action should be enabled. And for linear dynamics, that's quite straightforward, because we only have to kind of inverse this A matrix, one of these matrices of this system. But for nonlinear systems, this may be more difficult. And that's, I think, the main difficulty we need to consider there.
Okay, thanks a lot for these insights. So if there are no further questions, which I don't see at least, we should thank Tom again. Thank you. And the next presentation will be by Nilanjana Paul. I hope I pronounced this somehow correctly.
Yeah, it's fine. It's Nilanjana. Yeah.
Okay, wonderful, Nilanjana. She's a PhD student at Vanderbilt University working with Taylor Johnson. And I hope that you will be able to share your screen and show us your slides. Yes, I can see your slides now. So I think the floor is yours. Please go ahead.
Hi, everyone. This is Nilanjana. I am, as you mentioned, I'm a PhD student in the Vanderbilt University, and I'm working with Dr. Taylor Johnson. And today I will be presenting in the work in progress paper titled Safety and Robustness Verification of Autoencoder-Based Regression Model using Nnv Tool. So we have seen so far that there are many verification techniques, reachability-based and different other methods already work is done on feed-forward networks, convolutional neural networks, and RNNs and semantic segmentation networks, but almost little to almost no work has been focused on autoencoder-based models yet. So we explored this area of research and played around with some experiments, and that's what I'll be showing here. So the topics that I'll be covering for this presentation, it's a little background on how autoencoder works and how the verification, in general, how the verification works, and also using an Nnv tool. And then a little background on the adversarial attack that we used here. Then we go through the problem definition that we considered for this paper and some experimental details. And then I will end with a conclusion and some possible future works. To start with the autoencoder, it's basically a subset of artificial neural networks, which basically constructs the input at the output. And it has two main components. It's like the first part is the encoder and the second part is the decoder. So the encoder part compresses the input dimension to a lower dimension. So it can sometimes also, so only the encoder part can also be used for feature, to reduce the feature dimensions. And the decoder part then takes this lower dimensional space to a higher dimensional space, and which matches most of the time with the input dimension. And one question often arises: if an autoencoder works perfectly as an, like, why not a identity function, or does it actually work exactly as an identity function? The answer is no. It's intentionally trained to be not work perfectly as an identity function because of this overfitting and generalization error. And to make it more generalized, to generalize it throughout the trained and some unforeseen data, it's not exactly trained as a perfect identity function. And based on the learning objective, all the applications where autoencoder is used or neural network-based autoencoder is used, it has two main types: regression-based tasks and classification tasks. So for classification tasks, a regression autoencoder model is trained first, and then the decoder part is removed. And then it was replaced by a softmax and classification layer. And then the entire system is like trained again to make it like more efficient. And as in terms of verification, as the classification model almost work similar as normal other classifiers like feed forward or convolutional. So this is not the main concern for this work, and we are more focused on the regression-based works. And so the regression work is mainly to reconstruct what's in the input to the output. And some typical application for autoencoders are in data renoising, fault detection, etc. So the next step should be to know how the verification of neural network actually done conceptually. So if we consider set-based approaches, I think Stan has already cleared the ground for that, already explained in details, but it's actually what it does. It takes an m-dimensional input set, and then it passes through all the layers. And at the end, in the output, it creates an m-dimensional output set. And in classification models or in classifiers, the output nodes, they are equal to the number of classes that we have. And for verification of neural network, there is some properties that was specified. And then we check if the output set intersects with the unsafe region. If it intersects with the unsafe region, we say the system is unsafe. And if it doesn't, it's safe to operate for further works. So here we use the Nnv tool. It's a neural network verification tool, which is developed by the Very Vital Lab. And it's a MATLAB-based tool. And it's the approaches for reachability, it uses set-based approaches mainly. And it can take care of several neural network systems like feed-forward, convolutional, semantic segmentation, and some closed-loop neural network systems as well. So I'm not going much deeper into the neural network verification tool, then it will be a complete, the work is already done. If someone is interested, they can, I have the reference here and they can follow that. But in general, what it does, it takes the input, it works almost similarly as this one. And for this particular work, in Nnv, set-based approach called ImageStar was introduced a couple of, I think 1 or 2 years back. And it's an extension, or the understanding or the concept is same compared to the ImageStar. And we have used signal data here. So I have renamed it as Signal Star, but the concept is almost similar as the one-dimensional version of ImageStar or generalized star set method. So Signal Star is a tuple of 3 variables, C, V, and P, where C is the central signal or the actual signal, and V is the generator signal instances, and P creates the predicate. P is the predicate variables, and by predicate variables we means the bounds that we have for the input nodes or input parameters. So this bounds with each input parameter along with the predicates, the complete set of constraints. With the complete set of constraints, the optimizer will solve this all constraints, and it to get the next step or the next layer of sets. And so this is basically the primary stage of the exploration of autoencoder verification. So we started off with a basic attack signal. And in general, any unwanted modification in the input can be termed as adversarial attack. And here we have used the impulse noise in case of, as you can see in the image given here. And so what is the impulse noise is actually, it's a random occurrences of spikes for a very short duration, but relatively high amplitude. And so this is also called like spike falls. So the main problem that we tried to address here, it was devised with our collaborators in TU Munich, where the autoencoder verification is a part of a closed loop system. And we are not discussing the entire closed loop system here because it's the main concern. So the sensor takes some signal from some other devices, and it gets like instant signal values, and it passes it to the autoencoder. The autoencoder takes the time instant values and tries to recreate it in the output, and then passes it to the controller. But sometimes while the sensor is passing the sample data to the autoencoder, sample noises might get added up to the original data. And also most of the times the controllers are designed to work with specific range of input values for like voltages or currents. So if the signal or the faulty signal goes out of these ranges, the controller can malfunction and the entire closed loop system can collapse. So the task which we are concerned here with is to analyze how big a fault can be tolerated by the controller given an uninterrupted signal and the fault location or the specific time instance of fault and an acceptable upper and lower bounds. And then to analyze the reconstructed output of the autoencoder using the Nnv tool and its reachability methods, and then to define some measures that we can access, or we can assess how the fault will be tolerated by the controller or not. So these are some experimental setups. First thing is to synthesize the data set and train autoencoder model. And the data set was not like some publicly available or a practical data set. It is synthesized using a Simulink model or a dataset generator code. And each signal is consists of 10 time instance values, hence like 10 input nodes and 10 output nodes for the autoencoder. And it's basically a 5-layer autoencoder model, which has like this 100, 75, 50, 75, 100 in this respective layers. And as I have already discussed in previous slide, we have considered spike faults for this work. And in simple terms, the reachability analysis using Nnv is done with a given bound of attack. So the attack, we try to create an upper and lower bound, define upper and lower bound with respect to the attack around the central signal. And then the signal propagates, or the input set propagates through different layers of the neural network. Then the final output thus created the reachable sets of the model with respect to the input attack. And once it's done, then we compared like the unsafe region with the output model. And here the unsafe regions were specified in terms of the false signals or the spikes. And here we try to define two evaluation measures. One is percentage robustness. So the percentage robustness can be defined as the number of instances, time instances where the output bound is within the acceptable upper and lower bound of the controller, divided by the total number of time instances in this particular window. And an unrobustness grade, this failure grade can be defined as at a particular instance where the difference between the actual signal or difference between the acceptable range and the output bound in upper side or lower side is maximum, and then divided by the actual acceptable deviation. So these are one sample plot. The blue one defines the actual deviation or the bandwidth that's allowed around the central network or the uninterpreted network. And the red one is the actual upper and lower bounds that we got after the after we have an attack or after the reachability analysis is done. So this case, we can see the for every instance, the upper and lower bounds are within the acceptable limit. So this signal would be permissible to pass to the controller, and it should be safe to do that. And if we see in here, with the lower acceptable range, there are some instances where the output bounds that comes from the reachability analysis, it goes beyond this acceptable range. And we can see a time instance near about t equal 95, sorry, t equals 96. This goes like way beyond the acceptable range. And if we calculate the previously defined measures, that robustness, percentage robustness, there's like 5 different instances where the output range goes beyond the acceptable range. So the robustness should be for 100 total time instances, this should be around 95%. And the unrobustness grade for t equal 95, this goes way beyond this is a maximum deviation from the acceptable range. So we took the difference between the deviation and divided by the acceptable deviation from the central signal, which gives a value, it's not shown here, but which gives a value around like 1.5, 1.6. And so this is almost what I have for this presentation today. And so the conclusion and future work. So in a summary, I presented autoencoder verification using reachability approach. It has much to do, I think, in future, because this field is not explored much or not explored at all that we have known. But in future, we would like to add more data sets and try to generalize the verification approach, because this case, it's very specific to some case study, but would like to add more data sets and generalize it. And also to like diverge into more autoencoder based applications. And this is one of the 2 of main references that we have used. So yeah, thank you. With that, I've come to the end of my presentation. Thank you, everyone. This is my email address. You can send me any email you have, any question you have, and I'm ready to have questions.
Yes, thanks a lot for this wonderful and very interesting presentation. Again, please feel free to type your questions into the chat or the question and answer. I would like to know, how does your approach perform? Like, performance-wise, how quick is it? What are the obstacles you?
Now it's very quick because it's only like 5 layers and the data set is really simple. But I think as we explore more on other data sets or other real life data sets, it might get a little complex. But right now it's quick, it's fast.
And have you tried to access the problem with a different approach?
That's what we are trying next.
Okay. Yeah, wonderful. Are there other questions? If not, thanks a lot. And then we have a little break, 10-minute break, I think, before the next invited talk, and Tran will take over chairing the next session. So thanks a lot, and see you back in 10, right?
Yep. Hi, Bar, can you hear me?
Yes, I can.
Can you try to share
Just
your...
the screen. Okay, let's try that. I'm not very comfortable with Zoom, so that's a good idea.
You are in your office right now?
No, I'm in vacation. So.
Oh. Yeah, I forgot.
Yeah.
Tron, do you want to take over this confess login thingy, or doesn't it matter?
What?
Yeah, so I logged in with this confessed ID that was there for the SNR workshop. Do you want to take over, or I don't know what it does, or whether it matters?
So I think we should ask Stephen to panelists.
Stefan, you mean, or
Like Stephen, right?
Stefan Schopp?
Yeah. He's gonna be the chair for the session 3, right?
Exactly. So we should make him a panelist, or
Yeah,
I can also give him the login, because I'm not sure what happens if I log out with that thing. I hope the session will not crash.
You see my screen well?
Yes,
so-
we can. Yes.
I think we can take a 5 minutes break before we
Yeah.
come back.
Sounds good.
So since you are the host, Tran, I can probably log out with this cast login, right?
I'm not sure. Yeah, I'm not sure. Yeah, I'm the host right now. I think it's okay.
Yeah.
The problem is when it kicks you out, you don't know what the problem is. Is it you or is it somebody else?
Yeah,
So-
right
Yeah,
now
we
it's all-
figured out what was the problem previously.
Okay.
So
So where's your vacation, Mark? Where are you now?
Oh, I am. I'm in Europe, and it's
Europe?
good weather, great. COVID is a mess, but hopefully we'll make it through. Let's.
Great.
Yeah.
So you visit your family there?
Yeah.
Nice. So how long is for your vacation? It's gonna
Oh,
come
just
back.
the end of the week. I'm coming back at the end of the week. Hopefully, let's see.
thanks a lot for doing this from your holidays.
Oh well, I committed, so sometimes.
Wait for your industrial start.
But also Tron is also very accommodating, so I cannot say no ever. So that's good.
No, yeah, actually, yeah, I'm very excited about your talk because I want to know more.
Oh,
What do I want to
yeah,
do?
yeah, let's see how it goes. Yeah.
Okay, so I'm gonna take some water and then come back soon.
Okay.
See you.
See you soon.
Yeah.
Can we start now? I think we can start now, right? Or can you hear me?
Yes.
Okay.
Okay. I think we have 1 more minute, but okay.
Yeah.
Sure.
Can start early for like questions, things like that. So hello everyone, welcome back to SNR. So we are in the session 2. Please join me to welcome Dr. Bakhosa for his second talk on verification and control for autonomous mobile system. So Dr. Bakhosa has got his PhD from Arizona State University, and now he's a senior principal scientist at Toyota Research Institute of North America. So Dr. Bakhosa interested in formal methods, testing, falsification, and monitoring for CBS. And he's a developer of Adversarial, a very well-known tools for testing, falsifications, and monitoring of cyber physical system. And his tool is very well-known in CBS community. So let's join me to welcome Dr. Bakhosa for his invited talk. Bart, you can take over. Thanks.
Thank you very much, Stan, for the great introduction. So yeah, as Stan said, my name is Bart Hojam. I'm a senior principal scientist at Toyota Research Institute North America and located in Ann Arbor, Michigan. Before we start, I just have a quick announcement. I'm feeling somewhat under the weather, so please excuse any pauses or interruptions along the presentation. So with that said, let's proceed. Okay, so the Trina CPS group has 3 main areas of research. It includes formal methods. This is where most of the research activities are. We've worked in the entire spectrum of methods, from exhaustive methods such as reachability analysis to even theorem proving, and less exhaustive but more scalable methods, arguably more scalable methods, which are sort of these semi-formal methods where you compare output behaviors with formal specifications, and then you try to somehow fix the system or provide feedback to engineers to go back and look at this to repair. The second area is multi-agent control, and the third one is the planning in dynamic and uncertain environments. Okay, so let's present an overview of this talk. So we're going to look at 3 areas again. The verification of autonomous mobile systems. These are a specific subset of cyber-physical systems that are characterized as autonomous and mobile. And we will look into various approaches in verification or testing of these systems, either as a whole or in each of these components. And of course, each of these components may have machine learning components in them. So we'll look at pretty much similar to the talks we heard from Stan. What are some of the approaches that that let us deal with this scenario or this case? The second is, again, very similar to the talk from one of the previous presentations on risk-bounded control. So how can we navigate from a start position to a goal position with an autonomous mobile system while avoiding static and dynamic obstacles, which exhibit stochastic, well, they don't exhibit, but they can be modeled. Their motion can be modeled with a stochastic differential equation. And finally, I will introduce a platform or a system that may be useful to the community for as a benchmark problem for which methods can be developed. So this is a human support robot. It's an actual robot that Toyota makes for research, and it has a very nice, I think it's very nice simulation platform with ROS Gazebo. So that's, And I just wanted to state that a lot of this work has been a great effort from our 3 fantastic interns this past year, from Anand Balakrishnan from USC, Shakiba Yakubi from ASU, and Xiaodong Yang from Vanderbilt, and our collaborators and our other academic collaborators. So let's begin. So for system level testing, one of the ideas that has been very prominent for a long time is this idea of specification guided testing. And you start with some system level specifications. For example, for robotics, similar to the previous slide, we can say that starting from if you start from an initial position, then eventually you will, within some time bound and some time steps, you will reach a goal position. For another example of this is the formalization of the RSS responsibility sensitive safety rules that were developed by Mobileye and Intel, such as longitudinal safety for the ego vehicle. This formula looks a bit complicated, but essentially it's a function that takes into account 3 things. Given an ego car and a front car, we need to consider what is the maximum movement while braking, potentially for the front car. So this is the maximum acceleration. For the ego car, there is a maximum acceleration before the reaction time, before you realize that the front car is stopping. And then what is the slowest acceleration while braking that you can have. So essentially, if you take into account all these 3 different things, you should be able to establish a safe longitudinal distance. Now, there's another question on how conservative or this could be if you actually, so you have to play around with these parameters a bit so that you're comfortable in your example. But we've shown in these 2 papers that specification guided testing can generate a lot of interesting and unknown behaviors that you need to resolve if you want to proceed with the product. So the way these systems work is that you have some simulation. You're part of where you can have software in the loop or hardware in the loop components, and you generate an output behavior. This goes to a stochastic optimizer. You take also a specification. And in this stochastic optimizer, you can have a robustness computation engine, which takes the behavior and the specification and produces a value, which indicates how far you are from changing satisfaction valuation. So you can think of it as a tube around a signal, which tells you how far the signal can go without changing satisfaction or valuation. And once you enter this into a stochastic optimizer, then you can think that these stochastic optimizers will try to minimize this until you find undesirable behaviors and conduct fault localization. One problem which is very interesting is you end up typically in an industrial setting, you may end up with thousands and thousands of test cases, and potentially a subset of them could be falsifications. Still, making sense of all of them in a way that can be more productive would be a nice contribution. So explainability of results. Although there's been a lot of work in this direction, I think there's still room for improvement there. Now, going into components, the component level verification. One approach is a top-down approach, again with these high-level specifications that you can develop over the perception system, and then you can check whether they are satisfied or not satisfied. So one such formalization is time to quality temporal logic, TQTL, and a more recent extension of that is the spatiotemporal quality logic, STQL. These are extensions of MTL, metric temporal logic, but they also allow you to reason about discrete IDs and classes of objects, along with other set operations or spatial artifacts like bounding boxes, outputted by perception systems. So in this work, what we did was we developed a monitor that takes a specification and a data frame generated by the perception module to provide a Boolean satisfaction, so either falsified or satisfied. And one such example is consistent detection. So for all objects in the current frame that have high confidence, this is an example specification. If the object is far away from the margins, then the object must have existed in the previous frame too with sufficiently high confidence. And we ran this on a, I think MOOT data set. I'm not sure, I would have to confirm, but let me try to play it if I could. For some reason, it doesn't allow me to play it. Okay, maybe I need to switch to automatic, sure. Okay, so this, in fact, in this example, there are a lot of falsifications, but it shows that this type of specification can be checked, and it will allow you to automatically do this process. And once you have a library of specifications, you can sort of have this as part of the development process. Okay, the second part is if we go into what if these components are machine learning components, specifically deep neural networks, similar to what Stan was explaining earlier today. So with deep neural networks, you're giving a feed-forward, in this case, feed-forward neural network. You have some input domain and you have some unsafe domain that the system should not enter. And there are various methods, either over approximation or exact methods, that are able to generate this output set. And then the question is, does this output set intersect with this unsafe domain? So let's look a bit. So recently we had a paper in HSCC 2021 where we looked at this problem. And again, a lot of this is repeating from the presentation that Stan gave because it was very good. So I might repeat a bunch of it, but essentially the problem is that you have several layers, and you apply several operations such as affine mapping or the operation on the neuron as well itself. In this case, we're looking at ReLU neurons. So you have these two different linearities. And then for each layer, you compose these. For each neuron, you apply these transformations, and then you do the affine mapping. A big challenge in this work is finding the right set representation, because a lot of the algorithms then are basically going to depend on that. And so in this work, we're doing exact reachability analysis. So I think that's important to emphasize. And we use something called Facet Vertex Incidence Matrix, which is, as in the example shown, it is each facet is listed and each vertex is listed, and then you show if there's a relationship between the facet and the vertex. For this separate representation, affine mapping is very easy. The faces of the set do not change, only the vertices change with, so you multiply with a weight and bias and add a bias, right? And for the ReLU neuron, for each ReLU neuron, you have to consider that this two linearities intersect, or can the set. So you have to get it. You can think of it as being divided by a hyperplane. What this does is that for each, so once a hyperplane divides this, then you can generate these two new sets, and for all the faces that are not part of this new set, you remove, and so on and so forth. So there's actually a very efficient algorithm to do this for each neuron. but you still have this problem that you could potentially have a very large increase of sets from these types of operations. So as you increase the size of the input, or you may get into trouble. We tested this method on the Akasu system. This is a controller that consists of 45 neural networks, 300 real neurons. It has several inputs such as distance of ownership from intruder, angle to intruder relative to ownership, etc., etc. And then you have as an output a score of 5 actions: clear of conflict, weak right, strong right, weak left, strong left. And we tested on 10 properties, which you can think of these input-output specifications. And on the right, what we show is a cactus plot for properties 1 through 4. And you can see we did this analysis with all these different tools. Actually, Xiaodong did. And we can see that our tool is this blue line here. And it performs generally very well. The biggest comparison is, I think the closest comparison is with Rayleigh and Neurify. And in the worst case, we are slower than by 2.1 seconds. And in the best case, it's sort of a big difference between the two approaches. So for the systems that we have tested, this seems to work very well. Now, the next question that arises is, so what if we fail to satisfy some input-output specification? Can we do anything about it? So then we can think of possibly repairing the network. And one such framework is the following. You take this model that you've trained, then you do reachability analysis as previously discussed, and then you see whether there is any unsafe data domain. If there is unsafe data domain, you apply some correction, and then you merge this with the training data, and then you repeat the process through several epochs. For this, we have to note that it's very important to be able to do backtracking. So we should be able to find this bad set and find what inputs lead us to this bad set. And in fact, the output reachable set is not very important, because once we have these bad inputs, we can sort of run this in this framework, and it will generate us the training data. So what we don't need, it's not necessary for us to do exact reachable set. So this integration is done as follows. Before an input set as is processed for each layer, its safety is first verified with our over approximation method. And if it's safe, it will be discarded. And you can continue with the exact reachability method. So this speeds up considerably the process, because you're filtering out these unnecessary sets as you're doing your processing. We apply this repair process on the horizontal CAS DNN controller, and we see through this repair process how this unsafe set output represented in red is reduced, shifted until we arrive at a state. And after 11 epochs, we arrive at a output that is that does not have any intersection with the unsafe set. And of course, the problem of perception systems can be seen as the problem of verifying these machine learning components, where we've all seen this, where you take an image input, you do a small perturbation, and then it results into a misclassification of that object. And that is reachability analysis is also extremely important here as well. So the verification of, so CNNs have some interesting characteristics. They're much larger. You have an image as an input, which contains n number of pixels, and you have, 3 different colors or etc. So you have to watch out, because your input becomes very easily very large. So what we're doing in this case is we're looking at pixel-wise perturbations. And you have these real neurons again, but you also have max pooling neurons. And we applied, it's a very similar idea to the previous one. And we applied this to CFAR10 and VGG16. And we were able to show that this actually works very well as well. Of course, the time required is much larger, but still, it's still doable. Now, in cases where really time is a major issue, or computational complexity becomes makes the problem intractable, we can think of fast reachability analysis methods. Well, we're calling it that, but it's not that. It's actually an under approximation method. So we can set up, we can actually check reachability analysis only on the most impactful neurons. So for example, you can check the gradient of each of them, and you can rank them, and then you can consider only like the top 10% or the top, only the 1% of the neurons in a layer. And this is for VGG16. The gray background shows you the exact reachable set, and these red areas show you the under approximation with different relaxation factors. What is very interesting is that these provide a very good rough idea of this gray set, and perhaps can be used as somehow to gain confidence that the system, the network performs as intended. So this is also presented in this work in the bottom, presented here. So yeah, with that, I'm going to wrap. This work again was done with the Vanderbilt team, so Xiaodong Yang and Taylor Johnson, and with John Dong from University of Nebraska-Lincoln. The second problem is the risk-bounded control problem. In this work, again, we provide a method for control synthesis to start to goal motion problem in environments with static and dynamic obstacles, while bounding the probability of collision in finite time. So this in this work, we work together with Shakiba Yakubi, Georgios Finekos at ASU, and of course, my team members at Toyota, Daniil Prokhorov and Tomoya Yamaguchi. And as a core tool here, we're going to build on the theory of controlled barrier functions to develop provably safe controllers that can be computed on the fly. So we want something very fast, and we need to account for uncertainties when they're present. Uncertainties when the hard bounds on the magnitude are known. In the worst, these can be very conservative, or we can model the uncertainty with stochastic characteristics and have some probabilistic reasoning. So stochastic barrier functions, these are an extension of barrier functions to stochastic dynamical systems. So they allow us to extend the concept of barrier functions to stochastic dynamical systems. So consider a control system described with an ODE. X.R equals the f of r component and the g of r component ut. This can represent a model or a robot or a self-driving car. And we can consider a system defined by an SDE. Very similar, except that we have a noise component here. This can represent the uncertainties. And let's assume that XU defines the unsafe set in the augmented state of XRXO. So we have XU equals to all the values of X, such that this h of X function, which we will discuss slightly later, is less than or equal to 0. And we set a goal set for the state XR, which is essentially a set of points, a set represented the goals of the robot, which is this psi of XR less than or equal to 0. So previously, conditions on the evolution of SBFs have been derived to ensure that at any time the probability that the state of the robot is in the unsafe set for any tau greater than or equal to t is equal to 0. However, in this paper, we extended these results to enable design of less conservative risk-bounded controllers. So given a time horizon t and a desired upper threshold p bar, we can ensure that at each time t, that the probability of entering the unsafe set, pu, equals, again, the probability of entering the unsafe set for any bounded time in the future between t and t plus capital T, is so that it's less than some p bar desired value. So our goal is to find a UT, an input, such that XR reaches the goal set, and at each time t, PU is less than or equal to some p hat. So let's look at this first part. So we use a mechanism, in traditional barrier functions, you use Lie derivatives for computation of derivatives. So basically, Lie derivatives exactly describe the temporal evolution of a function or a variable. But it is clear from this equation that the Lie derivatives describe that in expectations. And there's a very interesting result from Oxendal in 2003 that is quite involved to go over, so I didn't include here, but you can look at this reference, and this gives us a mechanism to take this expression and to work with, make it in a way that we can compute it. So the idea is to design a barrier function bx based on h of x, using which we can predict an upper bound to pu. So the BF candidate needs to be twice differentiable. This is because of this second term here. So you have this, you need to be twice differentiable. For all x, b of x is greater than 0, and then for all x in the unsafe set, b of x is greater than, b of x tilde is greater than or equal to 1. So an example of a barrier function is so this is a circle centered at radius with radius 1, and the barrier function is the exponential negative gamma times h of x. So let's define a PB equals the probability. So this is the supremum within the time horizon that B of x tilde tau is greater than or equal to 1. And note that PU is less than or equal to PB. Right, because, and then we can find an upper bound to PB and hence PU based on the expected rate of growth of B x tilde t. And we can develop this theorem. So we can say that if there exists an AB greater than or equal to 0, such that for all x tilde, this infinitesimal generator of B with x tilde is less than or equal to negative a b x tilde plus b, then at each time t and at each state x tilde t, we have this conditional. So if a is equal to 0, we have pu less than or equal to pb less than or equal to p0 plus pt. If a is greater than 0, this b is less than or equal to a, which gives us this expression, pu less than or equal to pb less than or equal to 1 minus b0 times exponential to the negative bt. And if a is greater than 0 and a is less than b, then we have pu less than or equal to pb less than or equal to this expression here. And we note that this is less than or equal to p bar, so that now this potentially allows us to develop another theorem. And let's go to this. So we can develop stochastic controlled barrier functions, and we can say that if there exists a SCBF B of x tilde such that at each x tilde t, the control input u and parameters a, b greater than 0 exist that satisfy the following equations. So this infinitesimal, this part is for the infinitesimal generator less than or equal to negative a bx tilde plus b. Either a is equal to 0 and b is less than this, or a is greater than 0 and b is less than this value, or a is less than 0, then a must be between these two ranges. Then for all t, pu less than p hat, p bar holds. Okay, so now we are ready to synthesize the controller. So these previous constraints that we discussed can be combined with constraints with reachability based on a control Lyapunov-like function in an optimization problem with a cost that represents the other objectives. So we have the return the minimum, the control input that has two terms. So you have a positive definite here for Q. You have plus K delta, which is this Lyapunov term, Lyapunov conditions that pushes the robot to the goal set. And you have these two constraints for bounding the risk. So when A is not equal to 0, in order to make the program a quadratic program that can be solved efficiently, either A or B needs to be fixed. So quadratic programs typically can be solved in millisecond speeds, or if it takes longer, usually there's some issue there. And the program can include multiple sets of constraints with respect to multiple agents. So you just add them. We note that in more recent work, which I have not included here, because you have an issue here, because control barrier functions in general, they will generate, there might not be a feasible solution. So there's a way of putting slack variables in order to invalidate some of the constraints, but still provide a solution. In some applications, that turns out to be wanted. And so that's another thing that you can think that can be added to this to make it more flexible. And let me share an experimental result. Consider an AMS model using a unicycle model as follows. So this is a very simple model that this is a in a highway. So this is around in a highway surrounded by agents driving between the lanes, and we model these agents as with this equation. And the AMS should reach the center of the fourth lane while maintaining a safe distance with respect to other agents. So here, the unsafe set is this expression. We essentially want to maintain a distance with the other agents, and our goal is to run to this part. So let me switch the pointer and try to run this. So you see, we are the blue dot, and we are trying to move further. So here, the ecosystem is in trouble because it cannot find the right opportunity to switch lane, but then it finally does, and it is a success. So let's look at this a little bit more. So you see that at time 3 or 4 here, we have this risk value increasing very high. And this represents time 4. So this is time about 4 somewhere here. And you see that it cannot turn to the left, and it cannot, it sort of has to move forward as well. So you see that the distance between the robot and the obstacles is getting very close. So that's what's corresponding to this figure on the left as well. Okay. So that was it for the risk-bounded control. And third topic, so I just wanted to share with you the HSR robot, which is developed by Toyota, and it is used for human support. It's called a human support robot, and it's sort of self-explanatory. The idea is that a robot will help us complete common day tasks. tasks. I just want to see whether I'm sharing the sound as well. And if I'm not, if somebody could help me how to do that. Or perhaps it's not needed. It's okay. So I'm just going to share a couple of frames. So you have this robot which has cameras. It's the height is 100 centimeters, but it extends. It provides omnidirectional movements, and it has a gripper, etc. A telescoping body, etc. So I would encourage anybody who's interested in this to go to the humansupportrobot.org to get access to the model for ROS and Gazebo. You should contact either Tomoe Yamaguchi at toyota.com, Yoshiaki Asahara at tri.global, or myself, and we'll try to set you up with an account so that you can download the. But from my experience, the best part about this is that the documentation is excellent and very carefully developed. So it was really a pleasure for me to work with it. And I just wanted to share it with you guys. So getting the robot is actually a bit more complicated itself. So I wouldn't have that as an expectation initially. Okay, so let's look at the robot. So it has a microphone, a 3D sensor, a display, a head stereo camera, a head wide camera, has some power button. It has a very good safety mechanism so that to avoid any accidents. And it has laser range sensors, IMU, and bumper sensor, etc. So yeah, there's an emergency stop button, an access panel, and so on. And I think it gives you a good platform to put a lot of these components that we discussed in this presentation into an autonomous mobile system. Yeah. So many research groups have been working with it already, and you might have already seen it. In that case, I apologize for the repetition, but a lot of work has been shown for fetch and carry tasks. So the human support robot helps the elderly, it helps the disabled, and so on to complete day-to-day tasks. In this work, this is some teleoperation system that is being conducted using a VR device. So coordinated whole body movement. Okay, and I'm going to leave it at that. Okay, I wanted to acknowledge the following collaborators from Toyota: Tomoe Yamaguchi and Daniil Prokhorov; from Vanderbilt University, Taylor Johnson and Xiaodong Yang; from ASU, Georges Finekos, Shakiba Yacoubi, Keyvan Majd, and Mohamed Hakmedjad; and from USC, Joe Deshmukh and Anand Balakrishnan. That's it for my presentation. Thank you for your attention. I'll take any questions now.
Thank you very much for your talk. So which covers a lot of things. Thank you very much. And I think we are open for any questions from attendees. So you can post the questions on the chat Q&R. So yeah, so let I ask you some questions first before see if any questions from attendees. So can you go back to the slide 26?
Yeah. 1 second. Okay.
So my question is how you can examine the existence of SCB app function, like how to make sure that.
Yeah. So this is a very good observation. and essentially you can so you cannot. So this is the down really the so SCBFs are very good because they compute very quickly, but the downside is that the solution is good only if it exists. So in many cases you might end up with not a feasible solution. So what do we do is we can put in slack variables throughout this problem, and we can, so when you put slack variables, you allow the optimization function to compromise, essentially. Then you lose your guarantees, but you can think of it as minimizing risk instead, rather than generating a control input that satisfies the risk bound. Does that make sense?
Okay, so in that case, you say you're gonna introduce slack variables to compromise.
Yes.
If there are no existence of that kind of function, right?
Yes.
So can you explain a little bit more how that slack's gonna compromise that existence?
Well, when you add a slack variable to the constraints, you have to also add it here. This is very similar to the Lyapunov part here. Essentially, you are giving it think of it as giving it leeway to violate a constraint.
Mm-hmm.
That's what a slack variable achieves, and I can so the paper on this is accepted for CDC, but it was just recently, so we didn't have time to prepare slides, so I didn't include it here. But the idea is that, yeah, slack variables are sort of a well-known technique in I think in controls. So you can just it's not very complicated part on to add them. What we also extended this on, since I mentioned it, was we extended it when we're doing state estimation with something like Kalman filters, because with an autonomous mobile system, your readings, you have to have some sort of estimation technique going on, and you would like that this control approach could support that as well.
Okay, thank you. I have another questions, but not related to this work. So
okay.
I want to ask a questions about specification side.
Okay.
So actually, when you deal with like in the real world, right? So the autonomous vehicle, for example, they can react the chance of the scenarios, right? If there are some scenario coming, like the environment changes, things like that. So that means you design the system, you design an AV to react to that kind of events, right? And what I observe right now is most of specification language, specifically for like signal temporal physics or something like that, you can actually specify the requirements for your system, okay, in terms of states, variables, right? I can call it like state-driven specification language. But what do you think that in the future, when we want to design the system to react to some events, it would be better to have like event-driven specification language instead of state-driven specification language? What is your view about that, right?
Yeah, I think that's interesting. So here's the problem. Once you go from, let's say, engine, so testing, so for engine behavior, you go from like one-dimensional, two-dimensional signals, or etc., to the real world of driving, where you have so many possible variables and so many other situations. So that's really one of the issues why it's still, you don't see a lot of autonomy in cars nowadays, is because you just it's a very difficult problem. So what I think is that defining a set of assumptions, or a set of defining the plant, or defining the world, is really just as big of a problem as defining the specifications for the system on which to test it with. So there's very good work by Dr. Sashia at UC Berkeley. I think Verify is the tool that they've developed, that allows you to scenic and verify, that allows you to develop this, to paint this world that you want to test your vehicle with. And I think that is a step in the right direction. Event-driven testing is also excellent point. You know, what if you have a car to the right that is parked, and then you have a child passing? So you know, so how are you? You need to test various timings of that. You need to test various. So really the input is massive. The search space is massive, and finding a way to test it smartly is a very, very, very tough problem. But I think there's been good progress in that direction, and I think it's sort of a required component to making autonomy a reality, not just in driving, but in general.
Yeah. So I think right now the main problem with the state-driven approach is the state explosion problem, like you said, right? And when you come to verification side, you need to have a explicit model of the words you are working, right? But in the real world, you cannot have that kind of model. Then yeah. So in that case, when you deal with event, then I believe everything is focused based on the event, how you react to the event. Then I think you can compromise like the state explosion problems, or you can also allow the interaction between different agents, right? So I know there's Professor CR work about verification, about Sync. So he creates the whole words around one single autonomous car, right? But in the real world, we're gonna have multiple car, and sometimes your vision is not enough to take a safe decision. For example, if there are 3 cars and your cars cannot see the 3rd car, right? So you need to somehow communicate with each other. And in that case, I think event-driven approach is better. Yeah, that's why I asked my question.
Yeah, I think the scenic and verify can actually handle that somehow, but that so I think I've seen, like, you can have multiple vehicles, you can have it city driving to this pedestrian, cyclist, etc. And also there's an extension of Estadero that also allows you to do this as well. But I think I understand what you mean by event-driven, where you control, you know, there's some reaction between events, right? That you can set up as part of the search. So yeah, I think that sounds like a promising direction. It's just really, I think, more complete thought of the testing framework needs to be done,
so
because it's really a difficult problem, and you somehow have to choose smartly how to separate it out into tractable problems.
Yeah. So yeah, we have one questions from attendees. So in page 13, can you come back to page 13? So how are these deep neural network controllers trained?
Okay, so I think for this horizontal cast, I think this is a well-known benchmark problem that you have. So the controller, now this retraining process, if that is the question, is that you have some model candidate. So you start off with something, you do reachability analysis, you find out that there's an unsafe set. For this unsafe set, you take some representative points here and you apply correction. This correction is you're choosing a delta y such that the output does not falsify the specification, and then you're merging it into training data, and then you're training it again. For each epoch, you repeat this process until you achieve this this process. So did that help?
Yeah, so yeah, he said thank you. So we have another questions. So from Flipkern, so what are some properties, especially beside adversarial robustness, that a company like Toyota would be interested in verifying for neural networks? So what are some properties that you are, like, company like Toyota is interested in verifying for neural networks? So
yeah, that's a very good question. So Toyota is a very, very big company, and I cannot speak for all, but I can speak more about what our group likes to see. So these input-output specifications are very important. Temporal logics, so reasoning with respect to events and time, occurrence of events and time is extremely important. Now we're thinking of, can a lot of this, so a lot of work has already been done in the CPS hybrid systems but now I think there's a vast open space in this area of machine learning, where the problem is now sort of decidable, but you have this explosion problem which you need to deal with. So stability, safety, liveness properties. So all of the standard things that we've been talking about for a long time in hybrid systems, those are still very interesting. And if you're talking about, for example, various, for example, when in the past we worked with various engine systems or gears, powertrain, and so on. So you would have something like if the vehicle goes from the first gear to the second gear, then within some time it should not oscillate between second and first gear anymore. So this is just one possible example of a property that would be interesting to check, because or you could have more complex properties. But the idea is that we want to develop the mechanism for the developers and engineers to be able to specify these properties. And actually a big challenge there is making this process easier, because writing specifications is not something that is easy.
Yeah, I totally agree. So yeah, I want to ask some information about the questions from Philippe. So actually right now in neural network verification community, they are actually interested in more complicated reactive behaviors of autonomous agents that have learning enabled components like neural networks. So basically they don't not only sort of interested in safety or like reach avoid safety property or robustness properties. They also interested in, you know, the property like more complicated property, like, so when you have an autonomous driving car, right? So it's go straight forward, do overtaking, go straight forward, and do like overtaking again, something like that, like some behavior that can specify in terms of temporal logics, and they are looking for the methods to verify that type of system satisfy a more complex specification. So, and then I think Air Force already rise up like a project for that problem right now, as far as I know. Okay, so thank you very much. If we don't have any other questions, let's join me to thank you, Bar, for his great talk.
Thank you.
Thank you very much, Bar, for your talk. We appreciate that. So now we're gonna come to the third paper presentation from the University of Oldenburg, Germany. So my pleasure to introduce Dominic Grund. He's a researcher in Institute of for Informatic Technologies, Oldenburg, Germany, and he's going to present us a work on verification of SIG model artificial neural networks using ISAP. So Dominic, you can start right now. Thanks.
Okay, thank you. Hope you see my screen right now. Did you see my presentation? So please let me know.
Yep, that's look good.
Okay, thank you. Yeah, so indeed, my name is Dominic Grund, and I'm working at the Office Institute for Information Technology in Oldenburg, Germany, and together with my colleague Zorin and colleagues from the University of Oldenburg, Willem Hagemann, Paul Kröger, and Martin Frenzle, we are doing just a work in progress verification of sigmoidal artificial neural networks using the solver ISAT, and this work is supported by the German research project KI Wissen, or in English, AI Knowledge. So also for me, first motivation. Let's see, I'll share this. Yes. In the last year, the world wants to make use of the strengths of artificial intelligence to our advantage. And for example, one idea is to use the artificial neural networks as controllers for a cyber physical system, especially for the safety critical domain. And the goal with this idea is to reach a safer system behavior or overall safer traffic. And this is based on the fact that we can achieve a rapid analysis of correlations between the data, and we know the environment, the real world environment has a lot of data to capture, and it's very complex. And so we hope that we can achieve this with artificial neural networks. But if we talk about the safety critical domain of cyber physical systems, the system verification is necessary because in the worst case, it can hurt people, and that is something we don't want. And if we talk about the verification, on the first view, their internal composition seems to be quite suitable of neural networks because it's like a easy matrix multiplication, which is not that hard for the classical means. But on the deeper view, we see the activation function, which usually involves nonlinearity, or at least piecewise linearity. And this is extending the verification to such an extent, doing this difficult to such an extent that especially state-of-the-art SMT servers can't handle nonlinear functions like the sigmoid function with the good scalability. And we want to handle this problem a bit better with our approach. And on the first side, we want to use the solver ISAT, which is an SMT-based proof search solver, and it's combining the interval constraint arithmetic, constraint propagation, and those we can do reasoning about Boolean combinations of nonlinear constraints, also including transcendental functions. For example, we have the some constraint like the sigma of x is less or equal than y, or x plus y is greater than 3. And some extent of this. And how does it work? So we have an interval constraint propagation on this, and we're doing this through a step where we can't do any propagation further based on some constraints of the system, and then we do a splitting on the intervals and doing some SMT-based well-known methods like backtracking to get to solve the constraint system. And the possible results that we can get are, for example, satisfiable, but this is very rare in the context of interval constraint propagation with floating point numbers. So this is just possible when we talk about point value intervals. And then we have the unknown result, which bring us a candidate solution. Here we're talking about the semi-decidable domain because a candidate solution says, okay, this is a resulting interval. There can be a solution or even not, so I'm not sure. And an unsatisfiable is just saying, okay, there's no feasible solution for this constraint system. And if we talk nonlinearity and about ISAT, we decided to do something with the sigmoid function. Also to the fact that the solver ISAT didn't have a dedicated propagator for it. So what we do is we make use of the monotonicity and the totality of the sigmoid function on the top, on the right, and on the bottom we see the reverse function. Both have the same monotonicity and totality. And with this, easy we can use the intermediate Rayleigh theorem to get a dedicated propagator for this. And in doing so, we can just apply the sigmoid function or the reverse function on the upper bound, lower bounds of the intervals. And of course, we have special cases on the edges of the functions, but this can easily be handled, and we're doing so. And with this propagator, with a new propagator for the sigmoid function, we thought it's time to compare this first with our own propagators. Yeah, we see a first composed Sigmoid propagator, which means IZARD was able before also to calculate the Sigmoid function, but with the definition itself. So for example, we see on the left, that is the definition of the Sigmoid function, which ends up in a multiple propagation just for one variable because of the combination of basic arithmetics. With the new Sigmoid propagator, where we can say, okay, z is equal to the Sigmoid of x. We don't need to have multiple propagations. And we also considered the approximation approach because in the community and the literature, there's often the case that the nonlinear functions are approximated. So we want to show related to some other tools, which doing also approximation, how this approach will perform on a verification of neural networks with IZARD, or especially combination of interval constraint propagation with SMT. We consider two models. First, we introduce the European train control system, which is a real-world problem or a system that is running. It's a little bit simplified here, but it comes very close. And there are two trains on one track. Right on the right side, we see pointer right. Yes, on the right side we see the train in front and a following train on the left, and they have a distance between, and the distance is also called the absolute braking distance, and this is the sum of the braking distance and an additional safety space of 400 meters. And what we are doing is calculating the distance between the trains and also calculating the needed braking force to be in the absolute braking distance. And if the braking force exceeds the threshold of minus 0.7 meters per second, then we want to brake to get back into this window of smaller than or greater than minus 0.7 meters per second. And we also considered the well-known MNIST set, where we have handwritten digits, grayscaled, and with a size of 28 times 28 pixels and over 60,000 samples. And on the first study, we compared the runtime on the models with different experiments and different models, neural network models, in the sense of different numbers of neurons in the hidden layers, and also different number of hidden layers. And what we see here is on the left side, the runtime comparison between the composed approach and the new dedicated propagator. The orange line is marking the time points when the both propagators are on the same runtime. So one blue data point is containing the runtimes of both considered propagators in the same experiment. And also in this experiment, we are looking at problems which are not only about safety critical properties in the sense of verification like counterexamples or negotiation of such properties, but also just to find a candidate solution for known solvable problems regarding these models. And what we see on the left side, that in most times the new dedicated propagator was faster. And also on some experiments, we see that the new propagator having a solving time from about 80 seconds, where the composed approach already comes about over 1,000 seconds, or reaching the timeout cap of 5 hours, or at least 80,000 seconds. And an even clearer difference we see in the approximation approach, where we see the same behavior when we talk about 10 seconds for the dedicated propagator. The approximation approach is running into timeouts of 5 hours, and also often over the 1,000 mark. So for this takeaway is it makes sense to use dedicated propagators. And of course, if you talk about approximation approaches, there's already the trade-off between speed and also precisely accuracy or precision in the in the resulting intervals. Especially here, we see that also our new dedicated propagator is faster than the approximation approach. And further, we want to focus also on verification and a little bit more on safety verification. So for the ETCS model, we set the velocity between 20 meters per second and 83.4 meters per second, which is from the data sheet of the ETCS model. And we have said, okay, we have a braking force higher than minus 0.7 meters per second, so which violates the safety property, and asking is there an assignment that we get the decision don't brake, even if we are violating the safety property. And for the MNIST set, we have 3 verifications. First, it's called all. Check if an input digit has the highest prediction value of all digits. So it means we put in a 7 in the input, and the 7 should be the highest prediction in the output against all digits. And we have the single where we check the same, but just against another digit in the output. So for example, we put in 7, and this is has the 7 the higher prediction value in the output than an 8. And we have a fixed one where we check if an input digit has a low prediction value, or any non-input digit gets a high prediction value, also to see a little bit about perturbation and robustness. Yeah, for this we see on the left side the ETCS benchmarks. Also here the comparison of the 3 propagators, and in a time window within 4 hours we see that we were able with the new propagator to finish some verifications within 4 hours. So 50% of the models that we presented where we were able to decide something about. Yeah, we were by the other propagators we were by just about 25%. Why we're getting here multiple data points is also based on different neural networks regarding the number of hidden layers and neurons within, like before. On the right side, we see the MNIST benchmarks. Here we used, based on the runtime advantage of the new propagator, for the MNIST problem, we used only the new propagator. And here we allow a little bit fluctuation in the input. So the epsilon of 0.01 for every verification, and which means a first step in the direction of robustness and perturbation and adversarial. Very small, but a first step in this direction. And we see that we were able to have over 30% finish in the time window of 4 hours with a single with a single call verification, and for the others are 10%, which is not that much, but within 4 hours, and talking about variable numbers of about 2 or 3 million, that is very huge for an SMT solver, and for the floating point arithmetic, which is quite okay, we think. And so we are going on then with these results. We are also working now on optimizing IZAT itself for artificial neural networks verification, because we have a relatively long runtimes for problems that clearly violate safety properties, and we want to be able to handle just more variables than we thought, or the number of variables in a faster manner. And for this, we want to test different solving heuristics or new heuristics to get better through the internal presentation of the constraint system. And also we want to do some comparison with related tools. We also did something, but nothing that we share right now, or can share right now in this sense more. And looking forward to bring some benchmarks in the future compared to other tools. And with this, thanks for having me. And if you have any questions, feel free to ask me right now.
Thank you very much, Dominic, for your talk. So while we are waiting for questions from attendees, I have some questions for you.
Yes, of course.
So what are tools have you tried to compare your approach with?
Yes, so there are some tools, things back to 2010. There's the Nnv Tool, which are doing also some verification on the Sigmoid function with an approximation. And we are not comparing with it directly. We try to bring up the approximation approach of them a little bit, let's say, according to them into our tool, which is the approximation approach that I showed. Because Nnv was using back to 2010 the approximation approach, or the verification tool Hazard, which is a former version of the tool Hazard. So we thought this is a good idea to do some comparison against it, and but also with the cases back to 2010, which is a very big difference in years related to the computer science. We said, okay, this is we need more comparisons, and we also looked on Nnv 2.0, but it's a little bit hard to compare, to find a good comparison based to not be comparing apple with oranges, based on approximating approaches and also exact analysis. And we are looking forward to find more tools, and we know that we are not that fast like approximation approach or tools, but hopefully we can be one of the exact analysis tools that can handle sigmoid function or also other nonlinear functions in a good way. And I think there's a tool called PyNever, which is already accepted paper for the Advert 21 in October, and the tool is already on GitHub, free, and we are starting there some comparisons. It's also based on the works of Nnv 2.0, which are working with star sets and doing also some verifications on with the sigmoid function, and hopefully we can there find some good comparisons, and we show good results.
Thanks for that. So we have one question from Christopher Britt. Could the same approach be used when using different abstract domains for the over approximations that are more precise than interval propagation?
Yes, I think so. It's so first of all, this is very very early work that I presented here. It's we are not sure how capable ISAT could be. We think there's the good way, and we are already exploring some new, let's say, domains where we can apply this, because there are already this trade-off of being, is there a need to be that exact, or is a good approximation fine enough to make statements about safety properties? And of course, there's for other abstractions, abstraction domains, we can use this. And so with this said, we are going to exact analysis, and also like I showed, we did the approximation approach, and I think we can do something regarding other abstraction domains. Yes.
Okay. Yeah, thank you very much for your talk again. And then I think we're gonna go to the session 3 right now. So Stephens, you can take.
Yes, I guess you can hear me. I hope you can hear me. Yeah, welcome to the third part of SNR. In this part, we will have 2 talks. We will have one invited talk by Niels Jansen, which will be coming up now, and then we have a second part talk afterwards, concluding this workshop. Niels, can you? Yes, awesome. So maybe while you prepare, I'll quickly introduce you. So Niels did his PhD in Aachen at RWTH Aachen on counterexamples in probabilistic verification. He also did a short postdoc period in Aachen, and later on went for a year to the University of Texas, working with Ufuk Tokcu And since 2017, he's an assistant professor at the University of Nijmegen. And his research topics cover formal methods. And I think more recently, also dependability and safety in AI. And in his talk, Safe Planning under Epistemic Uncertainty and Partial Information, which I think we will be hearing today, he probably will dive more into that topic. Yeah, so the stage is yours.
Stefan, thank you very much. Can you hear me?
Yes.
Okay, perfect. So yeah, again, Stefan, thanks a lot for introducing me, and thanks for the organizers to inviting me to this very nice workshop. Despite it's online, it's been very nice, and I've listened the whole day, so this was awesome. So yeah, what I'm going to do today is talk a bit about our research, which I subsume in the talk, safe planning or epistemic uncertainty and partial information. And Stefan, you destroyed, I think, my start, as we will see, because I created a kind of a game about me. So this is 3 pictures from my career stages so far, and this just means that in Aachen it does always rain. In Texas there are cows, and in the Netherlands, as we all know, there are a lot of fries with frietensauce.
I think, did you mean to share a slide? Sorry for interrupting.
I should be sharing.
Okay.
Let me see.
Yeah. We don't see the slides from you.
Yeah, I see. Yeah, it's my problem. Excuse me. Can you see now?
Perfect.
Perfect.
Yes, works.
So here's my initial joke, which has been destroyed. No, it doesn't matter. So what I was saying that at this 3 stage that Stefan also already introduces. Okay. Much more important is to give credit to some collaborators that, of course, have been part of this work, and I decided to just list a few countries and universities that I worked with over the last years, from, of course, the Netherlands, US, Germany, Sweden, the UK, and Austria. Okay. More importantly, this is, of course, big credit goes to my group. So we see my 4 PhD students and my postdoc Sahara Buksh, who sadly has left, but luckily for her because she found a faculty position. And I co-supervised 2 students from UT Austin. And I think all of you saw Tom Bardings give a very nice talk earlier today about a different topic, but also somehow connecting to this uncertainty and dependability in artificial intelligence. So let us see. What is some safety, or if you want, so dependability in artificial intelligence? AI somehow has entered our everyday life. I list the standard pictures. So there's a self-driving car here, there's medical imaging, stock market, there's a Cylon from Battlestar Galactica, if you know it, there's a Mars rover, and other topics as well. And you also see some more academic examples like AlphaGo and some flight security. And what is important, I guess, that everybody recognizes that this AI safety or dependability is something very important. So, for instance, the European Commission says AI systems need to be resilient and secure. The Dutch Research Council says, how can we design trustworthy AI components with appropriate quality assurances? And roughly this is, I would say, part of our group's work. And let us now talk a bit on what is our, of course, very restricted view on dependable and safe AI, uncertainty, and its applications. After I did this rather, I would say, longer motivation, I will talk about 2 research highlights, namely some neural network policies and how to cope with data or epistemic uncertainty. Then we give a quick summary and outlook of what we plan to do in the future. So perhaps you saw in one of the initial slides this aircraft collision avoidance setting where we have 2 aircrafts. And this is basically depicting an AI decision support system. So what should happen here? Some AI should give advice to a pilot what action to take to avoid collision. Collision, we say, can happen if an intruder, for instance, another aircraft, enters the private space of an aircraft, which is indicated by the circle here. And this is based on current data, on current weather conditions, on whatever we may have at this stage. And we want to ensure safe decision-making. So the decision support system should give advice to the pilot that takes all these things, the data, into account and gives them safe advice for this. How do we solve such problems? So we work and we publish in rather lots of research areas, which is in this sense formal methods, in particular verification, rigorous verification, AI, in particular intelligent decision-making, control theory to aim towards optimal control, and also a bit in robotics, but mostly to draw case studies. So the question is now, what connects these areas? And from our secluded view, what does connect them is that we're all everywhere interested in safety and correctness and decision-making under uncertainty. So in all these areas, uncertainty is a central aspect. And I've looked for quotes, and one of them I found is that uncertainty is related to lack of predictability of events, stakes, or just a lack of data. So this is the kind of uncertainty that we want to deal with. And let's make this a bit more concrete. So uncertainty in this aircraft collision avoidance example. So what is uncertainty? It's in the sense we have limited sensing. There may be environmental conditions like, for instance, wind. The reaction time of the pilot may be slow, and the decision support system should take this into account. And we may just have incomplete data because we cannot send all the data. We don't may be dirty. We don't know anything. So the question is now a bit more refined. How can we ensure safe decision-making under uncertainty? And concretely in this aircraft example, what just does happen with the sensor limitations is that we may not actually know the exact position of the aircraft itself, and of course also about the position of the intruder due to all the factors that I mentioned before. And now we're interested in something more specific. We want to obtain the safety via uncertainty models. So we take a model-based approach. This again is in line with the Dutch research council, which says how to combine data-driven learning and model-based reasoning. And our central problem here is we want to learn or analyze a model from data or from samples that have been obtained by probing a system, and that robustly captures any uncertainty or probabilities that we can capture, and which is also amenable to efficient model-based analysis. So we have two aspects. We want to learn, we want to analyze a model, which we call an uncertainty model. We will see what our specific uncertainty model here is. So in our sense, we take a model which is kind of used in AI, in operations research, in formal methods, which is a Markov decision process, but it's a partially observable one, which means that an agent, or in our state, the aircraft, cannot observe its environment perfectly. And so we may, for instance, say, okay, we are at position X, Y, Z, we accelerate, and then with a high probability, we go to a position we want to, but because there are wind conditions, there's a low probability that we end up somewhere else than we envision this action accelerate takes us to. And for these models, as we've also discussed, despite them being around for long years, they're still, and they're being used a lot, still learning. A lot of them is recognized somehow an open problem because it doesn't really scale to realistic environments. We use a lot of applications for these models. More academic ones are standard grid worlds. We have some spacecraft motion planning example, which we'll actually see later. We have this aircraft collision avoidance. They, of course, they take some realistic scenario, but the data is academic, and we have more. We have some games we work with, for instance, with Pac-Man. We have some urban planning, but we also bring these models and their analysis methods to industrial partners. For instance, we work with paper scaling for industrial printer with Canon. We work on predictive maintenance of bridge structures, maritime fuel scrub replacement, and other companies as well. So this is something we really try to sell them. We have these models, we can analyze them, we can build them from data. So let's really work with them because we can get these guarantees if we have these models. Let us now go back to the more academic example. This is kind of a classic motion planning example. So the idea is we have a taxi and we have a passenger. We want to find the best way to the passenger. We also have to take some bad roads into account because it may be more expensive or infeasible to go over the bad roads all the time. Then we could say, okay, this is the best way because it's better to go over cracked roads than over gravel. However, we also need to refuel on the way, right? Because there's not enough fuel to go to the passenger. And we also need to account for some other kind of agents in the system, which in that sense are pedestrians or cyclists, which can move anywhere. So this may be the best way for us now, right, to refuel, but then we have to take into account that we still need to take the probably more expensive road over the gravel. But we also, to make it more complicated, have to account for a restricted view because these buildings, and we cannot really observe the pedestrians or the cyclists that may just jump in our way. And in our more formal method C scenario, we try to capture such things using temporal logics like linear time, logic or CTL, and also expected cost, right? So we have these two objectives. And then the formal problem is to find a safe and cost optimal policy to get to the passenger. And while doing this, we have to account for randomness and for partial observation. partial information, meaning that we don't really know everything because we have a restricted view, so we don't get precise sensor readings here. Okay, let us look a bit closer into this example. So what we assume is that we have some data on the movements of the cyclists and pedestrians. So we have some probabilities that they will actually jump in front of us. What we need is some efficient, dependable control, for instance, via neural networks of the taxi of the agent. We have a partial information, partial observability that induces an unknown system state because, as you see that the cyclist there, it may have many positions that we don't know. We just don't know. We just know it's behind the building. And of course, now I said we have these probabilities on the pedestrians and cyclists, but this also means we need to have acquired this data to get these probabilities. So we need to kind of collect this data in a safe way. We cannot just do trial and error here. Okay. So the underlying problem is now we have this partially observable mark precision process, the POMDP, and the form problem is find a provably correct and understandable neural network controller for a POMDP. These are a lot of buzzwords, so let's kind of dissect these settings now in the next minutes. This is kind of our very restricted view on AI safety. We want neural network controllers, then we need to ensure dependable decision-making and classification, and then ask ourselves, what is safety? When everybody says we're doing safety, so we want to be very specific here. For us, safety is really to fit something into some logic, some terminology constraint that is adhered to. We have partial information, so the question is now how to operate if the system state is not fully known, fully observable, and then what guarantees can we still give? Then we have uncertainty, and then the question is there, well, how to robustly, against this uncertainty, account for instance, imperfect sensor information. And of course, we will clarify this, what is robustness. I mean, people say this all the time, we are robust, neural networks, robust, but we would specify exactly what this is here. And this is our agenda of the whole group. Somehow this is, we work on POMDP policy synthesis and several variations. We work on neural network verification. We also work on safe reinforcement learning, but this will not be part of today's talk. And I'm generally always interested in some understandability, some people call it explainability, so to kind of make it accessible to a user what we are actually computing here. And kind of these four parts are now put into some general agenda that we're working on. So imagine we have some realistic case study. You see again the Google car, some bridges, some chips, you see some train networks. And from these realistic scenarios, we want to, via data collection, learn a model, or we may have some domain knowledge by which we can obtain a model. So this model is depicted here. And having this model, we want to then kind of get some results, right? We want to get some controller that makes some decision for us. And having this, we want to put this in a verification setting where we can say, okay, sure, we have our model, we have our controller, which may have been obtained individually, but I want to really verify, hey, is this safe, is this dependable for us? And generally, we're interested in making this a loop. So we want to say, okay, sure, we have verified something now, so what to do with it? So the answer should not be just yes, no, but the answer should also be how to improve something. So we may be saying we need to collect further data to reduce uncertainty. This is an example. As I said before, we're also sometimes interested in safe learning. So while we collect this data, we should be aware that the environment cannot just be probed arbitrarily, but we need to be careful with what we do here. And we also have some approaches where we put humans in the loop of some synthesis processes. So we take advantage of, for instance, humans' power of perception to solve some complicated problems, but again, within a verification loop. And this takes now kind of substance in several directions, which is work on neural network robustness, robust model synthesis and planning, safe reinforcement and process program, and also what I call kind of human model interaction, which other call, of course, human machine interaction, but I've never had a human interact with a machine personally. So this is that I did, but not in our research. So this is kind of what we call it here. Okay, so the outline is now that we will talk after this general introduction, what we do about neural network policies in a very specific setting, which is actually these POMDPs. So let us see. This is a POMDP, and what we see here is just a model where we have actions to like action A, up, down, to do something, and then we get probabilities on moving on to some states. And we have some constraints, like for instance, we want to maximize the probability to reach the state labeled as 7, and we also want to minimize the cost going to state as 7. These are these aforementioned neural network constraints. And what I want to tell you now here is that there are these colors. What do these colors mean? I'm trying to use my technical setup here. So these blue states mean that they share an observation. What this means practically is that whenever the system is in state S3, S4, S5, we cannot see this, we just see blue, right? So this means this may be different positions of the aircraft we had before, but we don't know that. We just know that this is blue. So this means we need to base our decision exclusively on this is blue, right? In the other states, it doesn't really matter. So what this means practically here now at the blue state, we need to decide, do we go up or do we go down? Yeah, okay. So let us say we choose up at each state. Yeah, so we do up here and here and here. What you see already that with up, we will reach S7 from these states, but not from this state. So this is kind of bad because there's a trade-off between these decisions. And this is called a memory's deterministic policy, deterministic in the sense that we will always make the same decision and we don't take any memory into account what happened before. So what we can achieve in the then is the probability 2 or 3 to reach the state S7. Right, so because we're excluding this choice overall. What we can also do, we can randomize this. And this is something very common, that's we kind of break the symmetry between decisions using some probabilities of randomization. So what we do now is we choose up with probability P, which is something between 0 and 1. And then we will get the probability 2/3 plus 1/3 times P, which can get arbitrarily close to 1. So this is better. Right? Because we break the symmetry between our decisions, we randomize. And I mean, in some sense, this is what neural networks often do, right? There's the softmax layers and these are randomized, then we fix the decision, but still internally, this can still be randomized. What is even better if we can kind of look into the past. So here, if the predecessor is yellow, yeah, we choose up. This is clear because if the yellow previous state was yellow, then we choose up here. If otherwise, in all other cases, we choose up if blue has been observed an even number of times, right? So 1, 2, and otherwise we choose down. And this is now because we can look 2 steps in the past. We know what is the best decision to make. And I mean, at this point, probably think about sure memory is fine, but this can be very, very expensive. You need to remember like decisions in millions and billions of states in the system, right? So this is to be treated carefully. But just to give you some impression on what we're dealing with here. So what we learned from this is that we can randomize, we can have memory, it can be deterministic. So what is interesting now, for POM-DPs, these partially observable Markov decision processes in general, if we want to get to optimal decision making, then we need to be able to randomize and we need to have infinite memory, right? So unrealistically, but theoretically true is that we need infinite memory because these trajectories of the system can go on forever. And this problem is naturally undecidable, but it yields optimal results in theory. What we can also do is we can say we can randomize and we can get finite memory. Then the underlying problem is NP hard. And now I always make the joke that it's also square root sum hard, but I don't really know what this complexity class means. It is very hard. It's also NP space. And then we're not optimal in general, but it's sufficient for many applications that we use. And we also discovered that in many, many benchmarks that are around for these models, actually you get the optimal decisions. Okay. Very intuitively, what we exploit is then randomization can trade off memory, right? So if you look at this toy example here, so we say if we saw blue 2 times, then we do red. If we do green 2 times, then we do orange, right? And then again, blue, blue, we do red. Now, what we say we do is, okay, we kind of have a feeling what occurs more often. And then we just make this. We do red in 2/3 of the cases and orange in 1/3 of the cases, right? So this is kind of trading off these sequential decisions and the memory, storing it by just randomizing. And this often helps. It's an interesting problem. I mean, there's of course also criticism to randomized policies. So yeah, this is can be a lot of debate. We exploit this. They can trade a memory for randomization. Our approach is quite a lot. Okay, let us see. So what is our general problem? By the way, I'm using a lot of colors now, but they become inconsistent over the talk because I didn't manage to make them all consistent here. We have a POM-DP and we have a specification, which can, for instance, be the probability of reaching a very bad state shall be at most 10%, right? So this is some specification that we can have. And then our problem is to find a policy. Then if we have this policy, we can apply it in our setting and then do some verification, model checking to say, hey, this policy and the model satisfy our specification. This is something we can really check. Yeah. So a very lazy approach now could be for us to solve our problems is, hey, just guess a candidate policy, apply this policy to a POMDP, to the model, and then do model checking, verification, any rigorous method that tells us, hey, this specification has been satisfied or not, right? So verification here is very efficient because we already resolved all the arbitrary decisions that we could make. But of course, we have no idea how to guess a better policy afterwards, right? So we need to guess again and again and again. And back then, when we started talking about these directions, I said, yeah, but I mean, everybody tells us machine learning is so great and can make all the decisions for us. So let's just somehow use machine learning, right? So this was our idea, that machine learning do the guessing. So let's say we can use a policy network here, a neural network that kind of represents a policy. And if we have this, then again, we can apply this policy, can do verification / model checking, and then, right, then we're there because it will always guess something good, which is not really true. We have 3 key requirements to this approach. First, it should be totally independent of the neural network architecture, or at least the complexity of the neural network. Because I've worked on myself and I saw a lot of approaches to neural network verification, and what we saw, if they are rigorous, like using SMT solvers or optimization like MLP, it always has like huge boundaries in what you can do. Because I mean, with so many layers and neurons and so on, it just becomes very complex and infeasible. Another thing for us was that we want to provide some means to improve and assess the level of training the network has, but formally using this verification. And of course, I mean, the overall problem, because we're talking about safety, is we want to obtain provably safe policies using this neural network. Okay, so you would probably guess this is a bit rather long wish list, but in this setting, it's rather realistic. So let us talk about what we did here. First, we used a recurrent neural network because we need to treat sequential data, but we will talk about this more. And then we extract a policy from this network, which was technically way more involved than we thought it would be. Then we applied this policy to a POMDP. Then we did model checking. If our requirements are satisfied, then we're done. But if not, then this now comes the interesting part here. We computed something that is called counterexamples. So verification, to some extent, does this as a byproduct, that we get a set of states that is critical to the specification, right? So this is numerical methods underlying, and they will, for each of the states, compute a probability that certain specs are satisfied or not, and this we exploit here. So for these counterexamples, we did some local improvement of the policy, which we will explain. So we just shifted the policy a bit, and then we used this policy to retrain the neural network, and by generating some new training data. We used the Keras library to do that. So this is a loop, yeah? I don't think I have it on slides, but what you already see, or what the natural question now is this approach complete? Can you guarantee to get to the optimum? And the answer is, of course, no, we cannot. This is a neural network, and we have no means to guarantee that we will find the optimal output, right? And I mean, the problem is undecidable in general anyway, so we will never be able to guarantee completeness, but we are sound. We are sound because we do this verification step here, right? So whatever we extract, we will be able to assess if this is a good or bad solution. And of course, in our experiments, it worked quite well. Otherwise, we would not be presenting this. But I mean, as with most machine learning approaches, you need to be a bit careful. There can be some outliers that don't work as expected. So let's look into some details. How do we learn these policies with recurrent neural networks? So what we do is the following. We employ an RNN with a long short-term LSTM architecture to learn dependencies in the sequential data. And why do we do that? I mean, you saw this example where we said, okay, we need to have a blue state before a yellow state or so on. So we want the sequences of inputs and outputs, right, to get these dependencies. So what we do is we train the network with observation action sequences of the POMDP. So this can, for instance, be opponent is far away, far away, far away, far away, near, right? And then what action did we take to get there, to get near the opponent if we have this competitive settings? And then we have a policy network, which is nothing else than a mapping from the sequence of observations from the POMDP to some action to take or to some distribution of actions to take if it's randomized. So in some technical talk, the observations are the input labels for the neural network and the actions are the output labels. So how do we improve these RNN policies? As I said before, we identify these critical states and thereby also critical decisions that lead to states with high probability of violating our spec. So for each observation with such a critical decision, we minimize the number of different critical actions by just solving some linear program. Just for this particular critical decision, it's a very small one. It doesn't guarantee anything global. We just believe, I mean, in the end, what it does is, so you have a certain system state, like this is my position, this is the opponent's position, the intruder's position, whatever. And we have this with 80% we choose this action, like accelerate, and 20% we choose another action. And we shift this a bit to something that we believe would be better to not reach critical states. And then we use this for it to generate more data, and then we train our network to do this. Yeah, and this works quite well. So we see this picture and a lot of experiments where here we have actually the number of critical states in our system. And here we have the probability of satisfying our spec. And this is iteration number. So what you see now that after some iterations, the probability of satisfying our specification, our safety spec, goes up. The number of critical states goes down. It will never go to zero because we are dealing with quantitative measures here. So this is always a probability to satisfy something, but it goes down, which is good for the overall setting. Yeah, so let us move on here. So this is what the result we presented at ICHCAI a few years ago. But what always bugged us a bit was that, hey, we have this neural network, which nobody can really understand. And so what we extract from this is a map of 1 million states and decision making and something, so nobody will ever be able to look at it, right? So nobody will ever to be able to do something with it. And that's so we said let's kind of streamline the extraction process a bit to something a bit more handleable for humans and also for verification. So this is the extract policy part where we put now 3 key requirements. It should be very good to verify, right? So no matter what policy we get, it should be easy to verify for us. The decisions should be kind of understandable, and we need to be able to really formally assess the training of the neural network. Then what we did for that was the following. Instead of just some big map, big file of policy, we extracted so-called finite state controllers, or we aimed to extract so-called finite state controllers, which are something for method people here, something like Moore machines where we have an input and an output. And so these are kind of understandable if they're not too large. And also we can kind of guide this, how large they are. And for these, we can again do model shaking very efficiently. And then another thing was, we said, sure, we have a neural network, but how do we know if it has been well trained? Does further training improve our policy? Or should we work on the extraction process to get a better policy? Then we said, okay, there's this information theory measure called the entropy. And we use this to kind of indicate the neural network accuracy. So in our setting, the following was, with a very low entropy of this model we have right now with the policy, then we think that we need to increase the precision of the extraction period, of the extraction of the finite state controller here. However, if we have a very high entropy, we kind of assume that all decisions are arbitrary. So for instance, if there is just uniform distributions of decisions, we believe that the training has not been sufficient. And we said, okay, we may need more training data. So this is some heuristic for us that enabled us to kind of assess the formal level of training. What is very important to us here, as we also see in the next slides, this finite state controller, this is a state machine. And we can just say, find the best FSC with 5 states that you can find, right? So we can just stop there after 5 states and say, this is how good we get. We need to understand what's happening. We can also say, hey, give it 1 million states, right? We want the best we can get. Nobody cares if the human understands it as long as the model checking works, right? So this is something we can control. And this was kind of an important aspect for me in this research. Let's see what are finite memory controllers or state controllers. So this is a POMDP where we have 2 observations. Let's say this is white, this is red, Z1, observation Z2 or something. And what happens just is the following. We are at a certain memory node, we see an observation, and then we go to an action, and then we go back to a memory node either here or here. Yeah, so this is just the kind of system that we're dealing with. Just asks, what observation do we see? Then it tells us what to do afterwards. And this can be fully randomized or not randomized at all. This is kind of a design choice. But why is this good for us to do? Because we can just put these FSCs into a POMDP. We can kind of compute the product of both. And then we get a larger POMDP where everything is without memory afterwards, because the memory is encoded into the state space. Of course, at the cost of getting larger models, this is for sure. But still, it works quite fine, because I mean, numerical methods can really scale up to billions. So this is, in this sense, a good approach in this setting. How do we extract and improve these FSCs? This was not something invented by us. This is a method called quantized bottleneck insertion by Kuhl et al. At ICLR a few years ago. So what this is in the end is just a discretization of the continuous memory structure of the recurrent neural network and a mapping to a predefined number of finite memory states. So we can really predefine the number. Let's use at most 6 memory states, and then we get the best we can get out of this number of memory states. In this entropy check I talked about, I mean, I depicted the formula here, but I will keep this part high level. So what we do again, we have these critical states that we saw before, and then we say, okay, entropy is high. We make arbitrary decisions. Then the neural network is like extrapolating decisions. If it's low, we still make strong decisions. Yeah. And then we need to increase the precision of FSC extraction because we assume that the network has been well trained. Good about FSC so far. So we have some experiments. I'm not going to bore you at this time of the day with a huge table. And we just wanted to highlight that what we can do is we can handle hundreds of thousands of states in the underlying POMDP, which just was not possible before, right? So at the cost of not being complete, not even having energy to approach the optimum, we can get very good results for our temporologic constraint problems here. Good. Then I promised to talk about epistemic uncertainty or data uncertainty. So what is epistemic uncertainty? It is an uncertainty that can, for instance, be coming from a lack of data, and that can be reduced if we collect more information. This is as opposed to aleatoric uncertainty, which, for instance, may be due to partial observability or partial information, or just the process itself. And so let us see. So if you recall this text exam that we had at the beginning, so then a big question that we very, very often get, I got since my PhD, I often didn't have a reply for that, is where do probabilities come from? They can, for instance, come from sensor readings, historical data, but the problem is usually they're all approximate probabilities. So what is a very common assumption also in techniques like reinforcement learning is that you just can somehow get point estimates of probabilities. So you have your probability 0.66 or whatever, right? And what we thought that this is kind of unrealistic because we should be able to account for imprecise probabilities. And so we not really developed, this has been around before, but we worked quite heavily in the last years on so-called uncertainty models, MDPs, POMDPs, with some dependencies, no dependencies, whatever. And here we talk about so-called uncertain POMDPs, which in some sense define an uncountable set of POMDPs. And then the policy should be able to account for all these POMDPs, right? This is a very high level view. And if you look at this example where you have these probabilities, here we do ranges of probabilities, we will see more. So these are so-called uncertain probability distributions. These are intervals of probabilities. And we then need to account for all these probabilities within. Form a problem, find a robust policy that accounts for uncertainty for a partially observable Markov decision process, right? So we make it a bit harder even now. Let us see. So what is this again, one of those models with these ranges. And now what we really want to solve in our setting here is want to find a memoryless randomized policy that satisfies our specifications and is robust against all possible probabilities from the uncertainty set. What is the uncertainty set? It's the set of these imprecise probabilities that we have here, right? These ranges of probabilities. And naturally, this makes the problem harder now. Let us see. So my favorite case study is a spacecraft motion planning example, which actually was created from some actual data and some actual work on spacecraft modeling. Of course, we had to do some simplifications on the way. So what is this about? Here's an aircraft. This is a satellite orbiting the Earth. What you see here are all the possible orbits, trajectories this satellite can do. What you see here are some objects that are in space, like trash, whatever. And now what we need to do is we need to orbit the Earth without crashing into these objects, without even having a risk of crashing into these objects, right? What the satellite can do, it can switch orbits, go to other trajectories here, but this consumes fuel. So what we want is, we want the satellite to orbit the Earth without having to change too often, yeah? Then what we have is we have partial observability over the actual position of the spacecraft. We have uncertainty on what the operators will do if we advise them to switch. We have uncertainty about the exact positions of the objects. So a lot of things are uncertain here, which you can probably imagine. And we will model this as an uncertain POMDP, and we will compute results, as we will see in a minute. Now I do a quick jump to an optimization problem. I'm not talking about everything in detail here. So for these uncertain POMDPs that we just saw, what you can always do is you can formulate your problem as an optimization problem. So what we do here is we want to minimize some cost, right? As I said, not changing these orbits too often. We need to satisfy, for instance, the probability of safely going around, not crashing into objects. So this should be at least some lambda. And we need well-defined distributions. So we need to be sure that always we have well-defined probabilities. We need to compute the probability of not crashing into some object. So this is what we do here. And I mean, I can tell you, of course, I could explain this in detail. Let's just have a quick look. So this is at a certain state, the probability of crashing into an object. This is the decisions we make. So at a certain state, we have a probability of choosing a certain action. And this here is the probability of taking that action and then going to a state. And this is the probability of the successor, right? We have something similar for the cost. And we also need to maintain some observation dependency. So this just says that if we observe the same object as far away, we do the same decision always because we don't know more. We can't observe the exact state. What is important to me here that we see why these problems are hard. So let us look into this in a bit more detail. Let's take a bit closer look. So what is this here? I said before we have these ranges of probabilities. This is what happens here. So this here is a concrete probability distribution, and this is an infinite set, an uncountable set of probability distributions defined, for instance, by these intervals or something else, likely convex set, uncertainty set. And this here is a multiplication of variables, of parameters. And this multiplication renders this problem nonlinear, and it's also non-convex. I mean, I've heard other talks about optimization problems, and what we all know that these problems are super hard to solve. So it's not really feasible to just give an optimization solver this problem and get a solution. It just does not work. So this is kind of our task, to make this amenable to more efficient methods. Let us see. Formally, we have a semi-infinite non-convex problem, quadratically constrained quadratic program. This is infeasible to solve directly, as I just also mentioned already. So the key factors that we observed here to solve these robust optimization problems is the type of the optimization problem and the type of the uncertainty set, right? So we need to do something about this and something about this, right? These are two things that we need to attack to be able to solve this problem. Let us see. I have like 8 more minutes, right? So I should be able to do that, I guess. Of course, I planned this exactly, so it will be 45 minutes. So what we do now is we work on robust synthesis for uncertain POMDPs, and we published this last year at ICHCAI. And so we have this uncertain POMDP, we have a specification, and we have the semi-infinite nonlinear, non-convex optimization problem. So the first step, what we do is we use some convexification method called the convex concave procedure to get a semi-infinite convex optimization problem, which is great, but it's still semi-infinite. So it's still an infinite number of constraints, right? So this is still a problem. And this is something I'm going to talk about now. This, by the way, joint work with Manik Soin, Murat Shubutek, and Ufuk Topçu. And so the next step was, let us a bit formalize what is the uncertainty set, what is our uncertainty. So let us now, and of course, people like Stefan know way more about what I'm going to talk now, like convex representation of sets. So I'm just a newbie to these things. So what we do is, we want to capture all valid probability distributions in these intervals. So valid distributions, we don't want invalid distributions, because then we would hugely over approximate the problem, and this would kind of make it still robust, but probably not really helpful in the real world. So we have these intervals, A1, B1 to AN, BN. And then what we do is we introduce a variable for each of these dimensions called DI. Yeah. And then these DI for all these intervals together define all valid distributions if we impose that they sum up to 1. Yeah. If we do this, then these DI overall form a convex polytope, right? As we see, for instance, here. So these are the intervals, and by some representation method, we can get these convex polytopes. What I wanted to highlight is the following. We see this polytope here, this triangle, this small one. We see this bigger shape, and we see this big triangle. What we should keep in mind now here, so the uncertainty is big here and very small here. But here it's also rather small, but we have a lot of these points, right? Of these corner points of this uncertainty. And as we see later, so this is kind of critical. So what we should keep in mind is that, this was a bad switch, that the shape of the uncertainty for us may be important. So we should be careful with what we do if we have access to reducing uncertainty here. So what we know is, if we have this uncertainty set, that robust, convex, quadratically constrained quadratic programming with polytopic uncertainties NP hard. Yeah. And for convex polytope, it is sufficient to enumerate over the vertices. So what we do here is, and for each of these vertices, we create one constraint that corresponds to this uncertainty variable, the underlying one. And what results from our semi-infinite problem is a bigger convex QCQP, which can be solved by Gurobi, for instance, right? So this is it's not linear programming, but it's convex quadratic programming. This can be solved rather efficiently by interior point methods. And what also is true is here now that the number of vertices, if we represent the uncertainty like this, is exponential in the dimension of the polytope, which in fact corresponds to the number of successive states in this uncertain POM-DP. And this was a general criticism we got, that this is an exponential blowjob of the problem. My answers were always, first, sure, but we couldn't solve it before. And second, in all the benchmarks, the models are rather sparse. So usually states don't have that many successors. So it doesn't really matter. Of course, we had some blow up, but it was still pretty decently solvable. And as I said before, the form of the uncertainty matters now here. So it's good to control this a bit. So for instance, say, okay, let's have some more uncertainty, but still be able to solve it, right? So this is an intricate thing that we can really control here. So where are we? We are in this solving this problem, and we have the semi-infinite convex optimization problem, and then we can restrict this to uncertainty convex polytopes, which is kind of a moderate assumption, in my opinion, because I mean we can always over-approximate the real uncertainty with some convex shape. Then we get a finite convex optimization problem, and we are able to then verify this by just solving the problem, right? We can iterate if we, in the convex concave procedure, we did something wrong, we can make this better. Still, this worked for some decent numbers of models, but we still managed to improve this further, as we saw and published this year at AAAI. So if we again have the semi-infinite non-linear optimization problem, we did some kind of dedicated dualization methods for this problem to get a finite non-convex optimization problem, which is of course even better to solve. And what happened now is that we did some linearization around some starting point, which we can get by heuristics. And if we have this, we just have to solve a linear program, which is of course very efficient. And if not, we can refine this linearization with a new starting point, right? So we create an iterative procedure here that gave us the means to solve these uncertain POM-DPs for rather large settings. So I promised to say more about the spacecraft motion planning. So what we were able to do is to solve problems with hundreds of thousands of states and transitions. We actually by now scaled it up to the millions by some tweaks in the implementation. And so what we see here is that depending on the memory that we use, we can get worse or bad results. I just want to talk about it. That meant what is important, that the amount of memory we spend on solving these is very important. And kind of the takeaway message is that we could solve these U-policies that are 3 orders of magnitude larger than previous approaches. Besides this, what was very interesting for me was really to look at the polys that we have, and this I do here. So remember this switch of the orbits in the U-poly piece. And what we saw, if we don't have any memory, if we cannot assess what happened before, where the objects were in space before, then we have to switch quite often, right? Because we cannot really know where we are because we didn't take into account. So this means the policy is worse because it has too much uncertainty, because we couldn't kind of determine the belief of the state by inferring from past decisions. If, however, we give it the underlying finite state kernel just 5 memory states here, 5 memory nodes, we only need to switch 1, 2, 3 times, right? So and this is really not fabricated. This is just what happened for us all the time. If we gave more memory and we could still compute solutions, then we get just way better solutions out of this. So this is kind of an important takeaway message that I want to show. And I think I'm basically done, and to be exactly on time, let me conclude here. So what I try to highlight is several points of our view to AI dependability and safety. And what I think is really important, so many people work on AI safety dependability and do great things. What I think is really important to really look into like really important shortcomings like scalability, data uncertainty, lack of explainability. And I'm not saying that we're solving these problems, I'm just saying we're trying to work into these directions. Current future work also involves direct verification neural networks. And I'm personally interested in more, say, problem-oriented research, where we can say what are real relevant safety features of a problem, what are real problems related to safety. I mean, we can always cook up these examples, but I mean, it's much better to really talk to somebody, hey, what is a real, like a robotics problem, for instance, that we could help to solve. Then I think it's very nice, would be very nice to introduce even more explainability to settings, for instance, to bring in the user by using some model-based or programming-based approach. So what does an engineer do? And they write a routine for how a machine should act, right? So this is an engineer's view. So this is a programming language. So why couldn't we bring our solutions to this programming language? So this is something that I'm really interested in. And of course, more in the modeling perspective, how to actually get or learn these models under uncertainty, right? So not just say, hey, we have this model, so let's do something with it. It's already how to obtain it in a formal way. Well, that's it. Thank you very much, and thanks for having me.
Thank you for the nice talk. It was very informative, I must say. And probably a payback, you solved many of my questions I already had, but we can still find some. This is also a call to the audience. So if you have any questions, please communicate them via this Q&A feature, and I will read them out. Until then, I think I also have some. Actually, you partially scratched it in your last slide, and also at the very beginning. So I was interested, what's your take on this, this safe learning? Because if I remember correctly, initially you need to somehow safely learn a model and uncertainties, and I mean that I would see as a kind of difficult thing to do, because you do not yet have a controller, right?
Yeah.
What's your take on this?
Yeah. So this safe reinforcement learning is kind of has become like a huge area from all kinds of communities, from the formal methods verification community, AI machine learning community. There's this direction of shielding, what people call also masking, whatever. My take is that to really guarantee anything, you need to know something, right? So what is of course interesting to say that you can, for instance, say, hey, I'm allowed to take some unsafe actions, but this gives a high cost. And if I do this up to, so in some sense, it's uncertainty again, right? So we have a lot of uncertainty and we reduce it by learning. And then the more we learn, the safer we connect. Or I've also seen, also worked on approaches where we say, we know the safety relevant features of the setting, but we don't know the overall setting, right? So we know what to do to act safely, but we have no clue what to do to act optimally. We need to explore this so that we could guarantee optimality at all time. There's also this these settings where we have fallback controllers that are always safe. For instance, braking the car. I don't know how safe this always is, but This is like the standard example. So unless you learn more, you need to just break down, right? So my take is to guarantee safety, you need to know something about the system at hand. Otherwise, it's a bit unrealistic. Yeah.
So the last case you mentioned actually that were these kinds of simplex architectures, right? Where you have
exactly.
something very conservative that is used as a fallback method, and then you can use it to as a fallback for your neural controller.
Exactly. Then you use the safe controller to learn more, and then once you have learned more, you can switch back to some more efficient method in the end. Yeah.
That makes perfect sense. I was wondering later on about the convexification. Can you give an intuition what it actually does? I mean, just because, so I know this from set-based methods, and they usually either over-approximate or you cut some set into pieces. Now, what was the intuition for your convexification?
Yeah, I can give a bit of intuition. I'm not no expert in this, but I roughly know how this works. So you have a non-convex function, and you split this function to a convex or concave part. So this convex non-convex part, and then you add some slack variable onto this non-convex part that you want to minimize, but still keep this part convex. So you kind of, in some sense, you put like a convex ring around this, and then you want to minimize this, or you over-approximate the non-convex part. So this is an iterative procedure where we actually where we included some verification loop, because this convex concave procedure does not converge very, very quickly, especially for our setting. And the convex hull around this non-convex part was too large. So we kind of got some candidate solutions, and then we used numerical methods to compute the exact outcome of this candidate solution, and then we could tighten these the slack variables around this. So this was the overall intuition.
So it combines over approximation and splitting.
Yeah.
There's a question.
Yeah. So hi Nils, thanks a lot for the talk. So I have questions about your vision about like different approach for verification. So I see in your talk that you talk a lot about model-based verification, right? So everything needs to be need to have model, right? But in practice, so we usually don't have model, and then you write the questions about how we learn the model, right? And is there any specific like techniques that you use to learn the model online?
Yeah, so so far I personally have mostly worked on model-based reinforcement learning, where we may have known some blueprint of the model, for instance, then assign some probabilities. What I'm really interested in is this direction of automata learning, model learning, where you, but then with probabilities. I mean, there were some recent efforts in the last years to learn these models actually, but they are very restricted to settings. And yeah, in the end, I really want to do some model learning with probability and uncertainties in the end. And I think it is a very hard problem, especially then if you also want to talk about safe learning. And also, I mean, the only thing you can ever get is statistical guarantees, of course, if you work with uncertainty. So this is, of course, a tricky part to do. But I think it's super important, because otherwise, at some point in the kind of data-driven world, this model-based verification will not help anybody, because we need to get these models somewhere automatically.
Yeah. So yeah. So I think So I agree with you about the limitation of model-based verifications. And if we think about how the robot actually work, right? So I do believe that most of verification technique right now usually cannot be applied directly to the real robots. The reason is that they don't have, like, usually they don't give you models, right? Or the models might be changed all the time. So yeah, I'm thinking about like how we can actually find another approach, like using like I'll say perceptions-based or LiDAR-based verifications or SLAM-based verification robots, right? So everything is probabilistic manners. And what is I believe the right way to do verifications for that kind of robotic system is start from where they are working right now. So they use probabilistic manner, right? So like for planning, they use RT, for example. It's very efficient, and everything is based on LiDAR, based on perceptions. Yeah, And I do believe that model-based design, I don't know how to actually leverage model-based verification in that type of system. So
did you say RRT star, or did I catch this correctly?
Sorry?
Did you say RRT star, or did I catch this incorrectly?
Yeah.
But I mean, also there are approaches that do include a model to instead of just sampling one trajectory, satisfying some, I don't know, some topological constraint. And again, this means that you have some form of a model that can control your sampling, right? So perhaps the solution is really at the intersection of these ideas. And about LiDAR, I think a few weeks ago I told my PhD students I really want some good case study involving some LiDAR technology, because I agree with you. I mean, this is the where we should look at into these emerging directions.
So actually I built some like autonomous driving car prototype in my lab, right? So we based on LiDAR and depth camera, things like that. And then the question is very obvious how we can leverage these things for verification, right? So we don't have model, everything is based on LiDAR data or perception data. So yeah.
Although Elon Musk would argue that LiDAR is not the future, right? There's this.
So I don't think that's I'm somewhat disagree with him. So I think LiDAR have some limitation, but we should combine like a depth camera and LiDAR together.
Definitely.
Yeah. So but everything is data driven, right? So and then we are from formal methods community. Everything is based on model, based on state, right?
Yeah, so what what I can tell you is that with our industrial partners, with some of them we just work with deep learning approaches because there's no real model. It's also a bit more about image recognition, so there's no real sense in getting these control modes that we do here. But with some of them, we had some master students working there, talking to all these experts, getting some form of model, which got super complicated in the end, as expected. And then there was no complete data, so we couldn't really assign any probabilities. But then we left these all open, and then we told them, hey, giving all the information that we got from you, we can compute this policy, this plan for you. And this was actually super interesting because, I mean, we learned a lot, they learned a lot from the model, so this can help. But there's a lot to do, definitely. Yeah.
Okay, thank you.
Thank you.
Thank you.
I don't see any questions.
That's all right.
Yeah, I mean, otherwise you can probably also contact Niels directly by email. You have a web page, so that should be fine. So thanks again for the nice talk. I would suggest that we advance to the next one, if that's okay with everybody. Otherwise, if you have still questions, you can also post them in the chat. And so the next talk, if I'm informed correctly, will be held by Luan Nguyen on model checking of rectangular automata via QBMC. And exactly, so that was a change of.
Yes.
So you're an assistant professor at Dayton, and this will be this work with your student and with Taylor Johnson together, right?
Yeah, thanks for the introduction, Stephen.
Yes.
So this is my talk today, the last talk, and so we went through a lot of the amazing talk today. So likely we come back to the traditional hybrid system after we learn a lot about the learning-enabled cyber-physical system. Yeah, so this is actually the works together with my student Wissam and my former advisor Taylor Johnson, and we try to perform the model algorithmic model checking for rectangular hybrid system using the quantify and coding approach. So let's go into the motivation and the overview of our work. So the starting point is that the SMT or the algorithmic model checking are very well known and have been developed to verify the high-speed system more than 2 decades. But typically, BMC perform checking using a possible very long but quantifier-free formula, and it's called the SMT solver to check for the query. And in general, most of the method is very expensive in memory usage because we need to explore the whole state space and whole of the transition relation. And there are the several tools, as well-known tool in our community like DRISH or HiCom, or even for partial using the SMT for the network of automata. And our motivation is we try to find another way to encode the SMT periodic model checking for hybrid system. And currently we stop at the time automata and rectangular hybrid automata, and we try to encode the BMC problem in quantifier form. And this problem has successfully applied to the purely discrete system where one can encode the quantified Boolean formula for the circuit, and that's called the solver to show the problem where the BMC is encoding in quantifier form. And motivate from that, so we try to encode the same problem for hybrid system, which we expect to have a very low memory usage and competitive runtime to existing tool. And in our approach, we will compare the quantifier encoding to some of the existing tools like the DRISH built on the real SMT solver, and the HiCom built on top of the new SMB using the Masa's FMT solver. And this is an overview of our contribution. So next, let me recall a very basic background on the SMT periodic model checking. And for the transition system, generally it varies from the initial setup state, right? And we also have a set of transition relation, which illustrates the transition between the state and some safety specification. And slightly, if we define some safety specification in negation of some Facet, and we say that it valid up to some of the step K if the query is satisfiable. And in general, the checking using the SMT solver, we can substitute the safety specification to the Facet, and we try to find to check it up to step K whether the query unsatisfiable or we receive the unsat result from the SMT solver. And it is a traditional SMT periodic model checking for transition system. And so we deal with the hybrid system. So actually, with one can be represented using the hybrid automata. And I just recall very traditional definition on the syntax of the hybrid automata, where we have the set of the variable corresponding to the set of valuation over the variable as well. And there the mode including some invariant and the flow that's characterize the continuous evaluation of the state variable. And there transaction between the different discrete mode of the hybrid automata and the set of the initial state. And this is a sample of the hybrid automata, which we call rectangular hybrid automata, where we see that the continuous update of the state variable is actually bound within some of the constant range from the, for example, here from A1, B1. And this model have a two discrete mode, log1 and log2. And actually we will have the time automata with the, if the lower bound and upper bound are equal, right? We have the constant value of a chain at the state variable. And we also have the multiple time automata. And actually with the A1 equal to P1 and A2 equal to P2, and otherwise we have rectangular hybrid automata. And again, this is the class of the hybrid automata we focus in this talk. And sometimes we can, this automata have some of the best state like that. If the system is stay at the log2, the value of the state variable less than 2.5. And actually it really happened, right? Because whenever the state variable greater than 2.5, we move from log1 to the log2, and we suppose that with the positive value for A2 and B2, so the value of state variable on way greater than 2.5. It's likely that if the system perform correctly, we will never reach into such kind of the best state. And we will use this best state for the further checking for the periodic model checking later on. Yeah. So the quantified free periodic model checking for hybrid automata are pretty similar to the quantified free periodic model checking for transition system in general. But the only difference here is that now we have a transition relation include both of the two different types of the transition. It can be the discrete transition between the discrete mode, or it can be the continuous trajectory evolving within the particular mode if it still satisfies the invariant of the particular mode. So it is traditional formula for the BMC's problem, and later on I will show the how we can modify it in terms of the quantifier. So let me take the deeper example how we can encode the BMC problem for the automata I showed previously, where we have two different modes and just only one of the state variable. And we just examine the quantifier free periodic model checking formula up to some of the small k equal to 2. And we see that at k equal to 0, so we start the initial state, where the location in the log 1 and the value of the state variable equal to 0. And here, if the value of k at the step k equal to 1, so particularly we will have a two type of the transaction. The first one is discrete transaction, where we can move from the log 1 to the log 2 if the value of s is specified in the particular range. And the trajectory, the T0 right here illustrate the continuous trajectory of the system. And we see it at the k equal to 1. So actually we drop the transition from log 2 to log 1 and continuous trajectory evaluation in log 2 because currently we are at the log 1 right now. But if I mean that if we encode the whole problem like the BMC query, maybe we need to include this because but this query unsatisfiable, so I drop it right here. And we can examine further at the k equal to 1. So actually the discrete transition cannot be happen because the value of S0 equal to 0 right now. So this is the unsatisfiable. So just only the continuous trajectory will be evolved at the k equal to 1. And let's move on to the k equal to 2. We still have we also have two different kind of the transition relation, but thing is different right now. So actually the continuous trajectory will not be satisfiable because it's possibly the value of s already equal to 5, and only the discrete transition will be happen that transit the system from the log 1 to the log 2 right here. So this is with a small step k equal to 2, just illustrate how the quantifier free periodic model checking for hybrid system encode in the traditional way. So the difference between the quantifier and quantifier free BMC and the quantifier BMC, we introduce the quantifier into the BMC encoding, and here we have the existing some set of the variable where Nnv0 define the initial state of the system, and here we have a transition between the different state of the system. It's a function over the valuation of variable right here. And in this formula, which we introduce the three new things. The first one, we need to have the real-time elapse in the trajectory, right? Because we deal with the hybrid system where in particular mode, we have the continuous evaluation of state variable. And we also have the time frame selector vector, and actually it associate what is the current state of the system and what is the next state of the system. And where the two assignment given to the time frame selected vector at some particular iteration of the periodic model checking. So this is show the very general quantified BMC encoding. And in the next slide, we show you how one can encode the time frame selected vector and assign the two assignment to some particular iteration. And so back into the similar problem for the discrete system, where the state encoding can illustrate in a irrelative form, and the transition between the state can be encoded there accepting the sequence of the state, and there is the transition between the previous state to the next state of the system. And so the encoding, the connection between the state actually can encode using the system of the two multiplexer. That right here where we have the selected vector. It's like the control input. Actually, some of the Boolean value, while with the size equal to the logarithm of k, right? And the setup state actually the input for the multiplexer, and the selection between the current state and the next state actually can be performed using the system of two multiplexer right here. And we adopt a similar mechanism to encode the state connection for the hybrid system. So this example just illustrate for you how we can associate with the different state. It's like the binary tree in the format where the Boolean value of the different variable t is right here associated with the current state of the system. And we see it. So for different part right here, for example, if the step the tree for the 5 input from the state from H0 to the F4. So with the state equal to the negative of the T1. And for this part, if the T2, we have the iteration equal to 5 and associated with this part. So we have a negative of T1 and T2. This will result to the state will equal to S equal to the current state equal to S2 right here. And showing into the binary form right here. And based on the value of the individual in the time frame selected vector, so we associate the current state of the system. And we also, this is just show only one of the merge on selected the current state. We also have the similar implementation for the second merge to choose what is the next state, the system. And using some of the time frame setter, actually we can review. We don't need to search for the whole connection of the different pair of the state space of the system, right? But here we can associate based on this Boolean value. We likely just we review the search for the connection, like the dimension of the logarithm of 2. Yeah. And so back into the example where we show you the BMC formula up to k equal to 3. And so if the k equal to 3 right here, so with the negative of T1, we associate the current state equal to the initial state, and the next state may be moved to the V equal to V1. And with the different selected vector right here, we show that the next connection between the state for the step k equal to 2. And similarly, we encode it into the T1 and T2 where the V equal to V2 and the next state right here is current to V3. And we add all of the set of the specification into the formula, very similar to the previous one. And it's k equal to 3. So back into the binary tree, I can show it. If k equal to 3, we see the bucket right here. We start at negative T1, and this part will involve the T1, negative T2, and T1 and T2 right here. But here in this hybrid system, the sample, so I just show you the k equal to 3, but it means that with the larger value of the k, so actually we will have a lot of benefit using the binary form of the selected vector to associate the state connection in the state space. So for the implementation, actually we implement it into the HIS, and with the current the initial input, we show the hybrid system in the state format. And the benefit of using HIS is that we can have some of the common environment just can produce the intermediate representation, and we just try to convert the same problem using the different tool. And it's very convenient for us to perform the comparison between the different tools, right? So we encode our approach to QBMC just compatible with the G3 Python API, where we can use the G3 as the SMT solver to check for the quantifier query. And all the sample report in the paper, and also the original code we upload in the GitHub. So if you are interested, you can learn more about how to use HIS and also our methods at the two GitHub GitHub links. I put it right here. So let's dig into the performance of our approach. And we still use the illustrative example I mentioned previously. And so here we have 3 different tools: our approach, the Dirichlet, and HighCom. Right? And we see that in terms of the time consuming, actually we are slower than the HighCom, but we very faster than the Dirichlet. But the memory consumption in our approach is significantly less than both of the Dirichlet and HighCom. So it's likely that we have a competitive time to the HighCom. And actually, and in current approach, we didn't use a lot of optimization, but the time maybe get better if we can eliminate some of overhead for using HIT, and that's called the G3 API. But in the memory, so particularly we aim to develop the approach have the lowest memory usage, and it show in the initial experiment. It's just our approach. Just for example, like K30 up to the 32 right here, we only need a less than 20 megabyte. While the HighCom may reach into the hundreds, and the reach is a similar amount of the memory. And we see that if we increase the step of the K, so our memory just increase a little bit more. But actually, some tool like the Dirichlet, so the memory usage is very huge if we increase the K to the larger value. So in order to take for the useful of our approach, we evaluate our approach using the larger benchmark, and here we use the Fisher protocol. And so actually we have 2 versions of the Fisher protocol. And to remind the basic idea of Fisher protocol, we try, it is a mutual exclusion protocol. So likely just the safety property is we don't want 2 of the process go into the critical section at the same time. So the best thing actually, if we define that there is a different process go into the critical section at the same time. And the Fisher protocol can illustrate using the time automata with the 4 different locations. And we have the 2 versions here. The safe version where the value of the constraint over the time variable, like A less than or equal to B, and the unsafe version, like the B less than or equal to A. And we examine all of the safe and unsafe version to verify the correctness of our implementation. And this in general show us our result to perform the boundary checking for the Fisher protocol and compared with the different tools. So we examine the Fisher protocol up to the 5 different processes. So it's likely the number of location is power 5 power 4 by here with a huge state space. And generally, all of the 3 tools return the similar checking result. For example, here if we go into the small project where the number of projects equal to 2, for both of the unsafe and safe person, and we quickly see that the results are similar right here. But we want to examine about the time and memory. Here, time in second and memory in megabyte. We see that. So, for example, for the safe person, so the time required for QPMC about 0.6 seconds is why in the HighCom is 0.5. So it shows that the HighCom is faster than us. However, the memory consumption us only need to require the 25 megabyte, while HighCom require more than the 100 megabyte. So significantly reduce the memory usage in now the QPMC approach. And compared to the Dirichlet, we outperform in terms of the execution time and the memory usage as well. And this is we go further into the larger state space, where if we have the 5 different processes for Fisher protocol, and you see that in for example, in the unsafe version right here, so we can the QPMC can show the problem with the memory only about the less than the 500 megabyte. Why the other tool so couldn't handle the PMC problem due to out memory. So, and here the memory limitation we put in about 4 gigabytes, so, which means that our approach is kind of very suitable and for the large system, which means it is scalable in terms of the memory usage. So, but again, so I want to emphasize again, our approach is still not faster than the existing approach like the HiCom, because HiCom still have a better performance due to the execution time. So we also take it with the larger protocol like the link service protocols, where the number of locations increase from the 4 to 9. Actually, link service protocol is the one of the modification of the Fisher protocol previously, where the property is time independent and with the higher degree location. And similarly, so we perform the comparison with our approach and HiCom. And unfortunately, the reach cannot deal with the link service protocol, so we don't include the comparison with the reach right here. But for the larger protocol, and we see the similar result, right? So why actually with the large step A equal to A right here, so we can show a problem with if the 4 processor right here, the PPMC can handle this with the memory usage about 700 megabyte right here, while the HiCom return that the out of memory notification. But in terms of the timing, for example, if we set the K equal to A, less than or equal to A right here, so with the 2 process, so QPMC require 5 seconds, while the HiCom require nearly about 133 seconds. So I think it's likely that we show that our approach is actually complementary to the existing approach. If we try to handle the large scale system and cannot be run with the HiCom, so we can try to use the quantified encoding approach we propose right here if we have the constraint on the memory usage. So let's go into the conclusion. So in our workshop, we try to propose a new SMT space technique that we try to encode the PMC problem using the quantifier. And right now, so we did the experimental for rectangular hybrid system, and we try to expand it into the general class hybrid system later on. And the result, initial result, like we say initial result, demonstrate that our approach is scalable and maybe in the future effective to analyze the very large scale hybrid system. And there is still a lot of the optimization we need to improve for our approach, and how we can encode the general class of the hybrid system like linear polynomial is still the things that we need to improve for the tool. And in order to improve our approach, we also want to perform additional experiment for other benchmark and cover a wide range of the application. And here we particularly focus on one illustrated example for rectangular hybrid system and 2 benchmark of the time automata. But definitely we will try our approach to other benchmarks, and we would like to compare our approach to other tools and techniques such as the UPRA or the tool built on top of CVC4 the solver. Okay, thank you for listening, and it's time for the question. Yeah.
Thank you for the nice presentation. Again, if anyone of the audience wants to pose a question, please feel free and use the Q&A tool. I have also some questions. You said you wanted to use more experiments and also compare to a wider range of tools, right?
Yeah.
I think, did you try the benchmarks? I mean, the Fisher, I think, is part of this benchmark suite in the ARC competition, right? So there's yeah. So there are some other benchmarks. There's also this tool Bach from Nanjing University, I think. It could also be interesting as a competitor, maybe.
Yeah, thanks for the suggestion. And yeah. Actually, I want to talk about the HIS tool previously. So previously, when we introduced the HIS, we come with a very wide range of the benchmark hybrid. So actually, it includes a lot of different dynamical systems.
Yes.
Linear polynomial, and we intend to use this benchmark for the future experience. But actually, right now we just stop at the current what the result I just presented today. But we know that we have a lot of the good benchmark from the ARC. I think from the group of Erica also have a good website for all kind of the benchmark for hybrid system, right? And from the history, definitely. So we try our approach on this also benchmark to evaluate more. Yeah.
I haven't. So right now there are no questions. I have two.
I have one question.
Yeah, please then go ahead. Sorry.
So, okay, so you say you're gonna invest the more general classes for hybrid automata, like you deal with linear or polynomial. So what is the harder things you need to show?
So actually the encoding is not hard. So we can use the similar encoding, but the key point is whether the SMT solver we implement and can handle this SMT query. So linear, definitely, I think G3 can handle this one, and even for the non-linear, but polynomial is very challenging. In this case, we have the huge, very complex way. So
maybe you need to go then to interval arithmetic, right? To FCP-based approaches like dReach or dReal does. Probably.
Yeah. Okay. And polynomial is usually we expect we have the same problem with the dReal when the number of polynomial grow. So it takes a lot of time in memory to show the BMC problem. So so one of one thing we want to investigate how we can modify the BMC problem. It's like to combine the BMC and IC3 problem in order to reduce the time consumption. And actually, it's not hard for us.
Again.
So in the iteration for model checking like IC3, right? So we don't need to perform the bounding or unrolling the step, right? Somehow we want to combine the two approach together, so it's to reduce the time and memory consumption. Yeah.
Yeah, I think try to encode with C3. I think that's the most efficient packet right now.
More efficient, I think the G3 because it's kind of popular and many people will use.
Yeah, most people use C3.
But I think another one is CVC4 is very popular also. I just realized that a lot of the people working on the SMT solver, so they use the CVC4 a lot and to build the tool on top of the CVC4.
So CVC4 is from Stanford, right?
Yeah, yes.
Okay, yeah, I know. Okay,
one technical question. Does the MOOCs you use, does it encode, I mean, does it differentiate between discrete and temporal transitions? I mean, since you already are alternating those, you can also reduce it again, right?
Oh, sorry, can you say it again, Stephen?
The MOOCs, I mean, basically you encode the bit vectors. By bit vectors, you encode transitions, right? And you, by selecting time frames. Is it already designed in a way that you will alternate time and discrete transitions? Does that?
So actually, no. So I think the way we encode the transition in the bit vector, like you say, and with the time specified in some of the line event, because the G3 support for the linear encoding, and actually it's very straightforward using the G3 API to encode this problem. So you don't need to do more complicated thing, but very straightforward. Yeah.
Thanks a lot.
And basically, the way we work is that we take the hybrid automata and some of the best stay at the input, and we try to write the Python code to automatically generate the query in the G3, and just call G3 to check the problem. It can it has been writing in very I think abstract way. So it's work with all kind of the hybrid system, and if you just the input the general the hybrid system is the space format, and some of the query specify about the best set of the system, and we just generate the query automatically and perform the checking.
No, that makes sense. Okay, are there further questions either from the panel or from the audience? I don't see any. thanks again for the nice presentation.
Yes, indeed. Thanks a lot.
Thanks a lot, Stefan, for chairing the session.
Was
So,
nice.
and you want to say something to conclude the conference?
No, you can finish.
Okay, so yeah, thank you very much for our participants to the conference. Yeah, thank you very much for your contributions. Especially, you know, we have a bunch of very interesting papers and invited talks. I really appreciate your time, your efforts to make this workshop successful. And hope you have a great semester, productive semester, and yeah, have a great week. Thank you very much.
Thank you, Tron.
Bye-bye.
Bye.
Bye-bye.
Bye.